Something lurks in the dark. Small, cold, watching. Not a monster, but something far stranger. A star. Just 7.9 light-years away, our silent neighbor in space. Tiny, dim, forgotten. But don't be fooled. If placed where our sun is now, Earth would burn, then vanish. This red dwarf, only a fraction the sun's size, hides unimaginable power. It flares without warning, violent storms that could wipe out worlds. Astronomers once thought it was harmless. Then came the data, unpredictable energy bursts, intense magnetic fields, and the terrifying truth. If Earth ever got too close, it would be swallowed whole. There's a star just 7.9 light-years away from us. That's right, less than 8 light-years, practically next door in cosmic terms. It sits there in the vastness of space, quietly glowing in the background of our galaxy. Not bright, not flashy. You won't see it twinkling in the night sky. It doesn't show up on your stargazing apps with any fanfare. It's just there. And chances are you've never heard of it, but you should have. Its name? Wolf 359. Yeah, it does sound like the name of an enemy fleet in a sci-fi series, and you wouldn't be wrong to think that. It has appeared in fiction, most notably in Star Trek, where it played host to one of the franchise's most infamous battles. But the real Wolf 359 is no invention of Hollywood. It's a genuine celestial body drifting through the cosmos, real as the sun, and possibly stranger. And here's the thing. It's small, like really small, and dim. So dim, in fact, that if you were to look for it in the sky with your naked eye, you'd never find it. Even with a decent telescope, it's a challenge. It hides in plain sight, closer to us than almost every other star, yet shrouded in obscurity. So what is Wolf 359? Well, it's what's known as a red dwarf, the most common type of star in our galaxy. But don't let the word common fool you. There's something almost poetic about red dwarfs. They're small and cool compared to our sun, often less than half its mass and burning with a soft, ruddy glow. But what they lack in size and showiness, they make up for in sheer longevity. These stars live longer than almost anything else in the universe. If the cosmos had a retirement plan, red dwarfs would be the ones cashing in their pensions 1 trillion years from now. Wolf 359 isn't just a red dwarf. It's one of the closest red dwarfs to Earth. Only a handful of stars are closer, the Alpha Centauri trio and Barnard's star. After that, you run into Wolf 359. It's right on the doorstep, astronomically speaking. But here's the strange part. How can something so close remain so invisible? The answer lies in its nature. Red dwarfs don't shine like our sun. They smolder. If the sun is a roaring campfire, then Wolf 359 is a glowing ember tucked under a log. It radiates less than 1% the light of our sun. That's not a typo, less than 1%. Even at a stone's throw in cosmic distance, it barely registers in our sky. Now think about that for a moment. One of our closest neighbors is almost entirely undetectable to us unless we go looking for it. That's unsettling in a way, and yet incredibly fascinating. What else might be lurking in the galactic shadows? Scientists love Wolf 359 precisely because it's so unassuming. It gives us a glimpse into the quiet majority of stars in the Milky Way, the red dwarfs that outnumber all others but rarely make headlines. And for science fiction writers, it's a dream. A hidden star, close to home, potentially dangerous, and possibly home to alien worlds. That's practically begging for a story. But this star isn't just a passive character in the galaxy's background. Oh no, it's a wild card. You see, red dwarfs like Wolf 359 are known for being temperamental. Despite their quiet appearance, many of them, especially the younger ones, can erupt in sudden, violent flares. magnetic storms that send radiation tearing through their planetary systems, capable of stripping atmospheres and sterilizing surfaces in minutes. Picture a bonfire suddenly spitting flames in all directions. That's the dark side of red dwarfs. Small, but not safe. So the question arises, could Wolf 359 be dangerous? Not in the way you might think. It's not going to go supernova and swallow us in a wave of fire. It's not going to turn into a black hole and vacuum up our planet. But given the right, wrong circumstances, it could send out bursts of radiation strong enough to fry nearby electronics, and if Earth happened to be in the path of an especially violent flare, it might be bad news for satellites, communication systems, or astronauts caught outside Earth's protective magnetic field. But that's just scratching the surface. Here's a thought experiment for you. Let's say, somehow, Earth was moved into orbit around Wolf 359. What would happen? Well, first, we'd freeze. Its feeble light would leave Earth in permanent twilight, like living under a dark red sunset. Photosynthesis would break down. Temperatures would plummet. The oceans might begin to ice over. Life as we know it would collapse. And yet, tucked in close enough, maybe 1% of the Earth-Sun distance, some form of life might still cling on. In fact, planets in tight orbits around red dwarfs are one of the hottest topics in astrobiology right now. So could Wolf 359 host alien life? Maybe. It's not impossible. In fact, astronomers have been scouring the space around red dwarfs for exoplanets because they offer one tantalizing advantage. Their dimness actually makes it easier to detect planets. When a planet passes in front of a red dwarf, it blocks a proportionally large amount of light, making detection simpler. So far, no confirmed planets have been found around Wolf 359. But that doesn't mean they aren't there. We just haven't seen them yet. And if a planet were orbiting close enough to be warm, but not too close to be scorched by flares, it might have the right conditions for life. Not our kind of life, maybe, but something strange. Something evolved to bask in the red glow and ride out the flare storms. Then there's the time scale to consider. Wolf 359 is just a baby, cosmically speaking. It's only a few 100 million years old. Our sun is over 4.5 billion years old. So in that sense, Wolf 359 is like a toddler with a sparkler compared to a middle-aged adult with a steady campfire. But here's the kicker. Long after our sun burns out, long after Earth is reduced to a frozen husk or vaporized in a red giant phase, Wolf 359 will still be there, quietly glowing, for trillions of years. That's not poetic exaggeration. Red dwarfs can live that long. Some scientists believe the last visible lights in the universe might be red dwarfs like Wolf 359, still flickering in the endless night long after everything else has gone dark. So when we say this star could outlive us all, we mean it, literally. All this from a tiny red ember floating just 8 light years away. It's a ghost in our backyard, a cosmic paradox. So close, yet so hidden. So dim, yet so enduring. So small, yet packed with mysteries. And that's where our journey begins. Over the course of this documentary, we're going to peel back the layers of Wolf 359. We'll dive into the life and death of red dwarfs, explore the science of stellar flares, and confront the big questions. Could this little star hide alien life? Could it teach us how to build interstellar civilizations? Could it, one day, be our last refuge when the rest of the galaxy fades? So buckle in. We're heading into the quiet fire of the universe, and it all starts with a star you've never noticed, but absolutely should. So, we've arrived. Wolf 359. Not a name that rolls off the tongue like Sirius or Betelgeuse, and definitely not the kind of star you'd notice shining in the night sky. In fact, even if you stared directly at the spot where Wolf 359 is located, you still wouldn't see it. Why? Because Wolf 359 is shy. It's one of the faintest stars in our cosmic neighborhood, and yet it's one of the closest stars to Earth, just 7.9 light-years away. That's practically our solar system's version of across the street. But what exactly is Wolf 359? Why does this tiny, quiet red dot matter so much to astronomers, science fiction writers, and now you? Wolf 359 belongs to a class of stars called red dwarfs. More specifically, its spectral type is M6.5. Think of that as its stellar personality profile. The M tells us it's a red dwarf, and the 6.5 tells us it's on the extreme cooler end of even that category. Now, when we say cool, we're not talking about attitude. We mean temperature. The surface temperature of Wolf 359 hovers around 2,800 Kelvin. That's roughly half as hot as the Sun's surface. If our Sun is a white-hot blowtorch, Wolf 359 is more like a glowing ember, radiating a soft, reddish heat. In terms of size, it's even more dramatic. Wolf 359 is just about 9% the mass of our Sun and less than 15% its diameter. If you put both stars side by side, the Sun would look like a beach ball, and Wolf 359 would be a small marble beside it. Humbling, right? And here's where things get interesting. Despite being only the 5th closest star system to Earth, you can't see it without a telescope. That's how faint it is. It's barely above the threshold of visibility and only under the clearest, darkest skies with the right equipment. Red dwarfs are like the introverts of the cosmos. They're small, they're quiet, they burn their fuel slowly. While massive stars live fast and die young, collapsing into supernovas and black holes, red dwarfs like Wolf 359 live long, uneventful lives. How long? Try trillions of years. That's right, trillions with a T. Our Sun has an estimated lifespan of about 10 billion years. Wolf 359 will outlive it by a factor of 100 or more. It's only a few 100 million years old now, a toddler by cosmic standards, and yet it's already destined to be one of the last stars still glowing when the universe is old and cold. That slow-burning life makes red dwarfs fascinating in their own quiet way. They're stable, stubborn survivors. But don't mistake stable for boring. Even introverts have outbursts, and Wolf 359 is no exception. You see, it's not just any red dwarf, it's also a flare star. That means it occasionally experiences violent eruptions of energy from its surface, solar flares, if you will, that can increase its brightness by several magnitudes in just minutes. Imagine this. You're floating in a nearby spacecraft, watching a quiet crimson dot. Suddenly, bam! A powerful pulse of light and radiation bursts from its surface. It's like the ember suddenly flares up into a mini firework, then settles down again just as quickly. These flares are caused by magnetic activity inside the star. Despite their size, red dwarfs have intense magnetic fields, and when these fields get tangled and snap, much like rubber bands, they release massive amounts of energy. These flares can be hundreds of times more energetic, pound for pound, than anything our Sun throws out. Now imagine you're a planet orbiting Wolf 359. One moment, you're soaking in a faint red glow. The next, your skies are lit up with lethal radiation. Not exactly an ideal spot for a summer vacation, or for life as we know it. But more on that later. So why haven't most people heard of Wolf 359? It all comes down to its luminosity, or rather, its lack of it. Wolf 359's luminosity is only about 0.1% that of the Sun. That's not a typo. If the Sun were a blazing 100-watt bulb, Wolf 359 would be a dim 0.1-watt nightlight. That means it emits barely enough light to register, even though it's one of the closest stars to us. It's this contradiction that makes Wolf 359 so intriguing, incredibly close, yet virtually invisible. It's like living next door to someone for years, only to find out they're quietly harboring a strange and powerful secret. Now let's talk about how this hidden neighbor was found in the first place. The name Wolf 359 might sound like a villain's coordinates from Star Trek, but it's actually named after German astronomer Max Wolf, who catalogued it in the early 20th century. He used photographic plates to detect stars with high proper motion, that is, stars that visibly move across the sky over time. And Wolf 359 moved fast. Its position in the sky shifts enough to notice over just a few years. That caught Max Wolf's attention and earned it a place in his star catalogue as entry number 359. No mystery code, no alien numbering system, just a catalogue entry with a last name. So who are Wolf 359's neighbours? Well, it shares its cosmic cul-de-sac with some familiar names: Proxima Centauri, Alpha Centauri A and B, Barnard's Star, and Lumen 16, a binary brown dwarf system. Despite its proximity, Wolf 359 doesn't form a binary or trinary star system like some of its neighbours. It's a lone wolf, pun fully intended, drifting solo through space. But that isolation, that's part of its allure. A quiet red ember, moving on its own, occasionally flaring up in bursts of temper, surrounded by cold darkness. There's something almost poetic about it. What makes Wolf 359 truly remarkable is that it offers us a glimpse into both the past and the future of our universe. From one angle, it's ancient in terms of design, an example of the earliest, simplest type of star formation. From another, it's still a young star with most of its life ahead. And billions of years from now, when our sun has long burned out, Wolf 359 will still be shining, dimly, stubbornly, like a single candle left burning after the party is over. Imagine that. Our descendants, or whoever inherits the cosmos, looking up into a sky where all the bright stars are gone, but Wolf 359 still glows. And that's the quiet power of red dwarfs. They don't scream for attention, but they endure. And in the great cosmic race, sometimes the tortoise doesn't just beat the hare, it survives the entire track. Okay, so it's small, it's dim, it flares up sometimes, and it's close by. But why is Wolf 359 worth more than a passing mention? Because it forces us to rethink our assumptions about stars, space, and even ourselves. It challenges the idea that the most powerful things are always the biggest or brightest. Sometimes it's the tiny things, the ones hiding in the shadows, that shape the universe in unseen ways. Wolf 359 may never host a habitable planet. It may never go supernova or light up the skies like a cosmic celebrity. But it will outlive nearly everything we know. It's a lesson in cosmic humility, in patience, in endurance, and it's not alone. Because here's the thing, red dwarfs like Wolf 359 dominate the universe. They make up an estimated 75% of all stars in the Milky Way. That's right, 3 out of every 4 stars you can't see are probably red dwarfs. So if Wolf 359 is just one of these cosmic ghosts, what else is out there? Could some of these faint stars harbor planets? Could life, maybe even intelligent life, be quietly orbiting a tiny, dim ember far from our gaze? In the next section, we'll dive into that very question. Could Wolf 359 host life? Or is it the ultimate cosmic trap, luring us in with mystery and hiding lethal secrets beneath the surface? When we think about stars, our minds often go straight to the sun. It's bright, it's warm, and it fuels life on Earth. But what if I told you that there's a whole class of stars out there that are, in many ways, stranger than our sun? These stars are called red dwarfs, and they make up about 75% of all the stars in our galaxy. But don't let their quiet, humble appearance fool you. They're weird, they're fascinating, and they're incredibly important for understanding our universe. Red dwarfs are the smallest and coolest stars we know, and their oddities start right there. Unlike our sun, which has a surface temperature of about 5,500 degrees Celsius or 9,932 degrees Fahrenheit, red dwarfs shine at much cooler temperatures. Depending on their size, these stars burn at temperatures between 2,500 to 4,000 degrees Celsius, 4,532 to 7,132 degrees Fahrenheit. To put it into perspective, that's more like the heat of a red-hot ember than the blazing surface of the sun. This low temperature is one of the things that makes red dwarfs so interesting and so different from stars like our own. But the weirdness doesn't stop with their temperature. Red dwarfs also burn fuel at a much slower rate. While our sun fuses hydrogen into helium at a fast and furious pace, red dwarfs do it at a much more relaxed rate. This is why these stars live for such astonishingly long periods of time, much longer than we can even comprehend. Think about this. Red dwarfs can live for trillions of years. Trillions. To put it into perspective, our sun is expected to last about 10 billion years. Red dwarfs can easily outlast that by a factor of 100. They're so efficient in their burning that it takes them an age to burn through their hydrogen, which is why they can stick around far longer than most other stars. This slow burn also means that red dwarfs are incredibly stable. In fact, many astronomers consider them to be the most stable stars in the universe. It's as if these little guys are the tortoises of the stellar world. They keep on going, slow and steady. In a way, they're the opposite of the sun. While our sun will eventually swell up and burn out in a dramatic, fiery death as a red giant, red dwarfs keep a much lower profile, and their eventual death will be slow and uneventful, turning into a cold, faint, and dim white dwarf long after most of the galaxies have faded away. Now, let's talk about something that adds a little unpredictability to these stable stars: flare activity. Red dwarfs are notorious for their flaring, which is a violent outburst of energy from their surface. These flares are similar to the solar flares we sometimes see from our sun, but red dwarf flares can be much more intense and frequent. Imagine a star that might erupt with the force of thousands of times more energy than a solar flare from the sun. These explosive events can last anywhere from a few minutes to hours, sending bursts of radiation and high-energy particles into space. While these flares might sound spectacular, they can be dangerous, especially for any planet that might be orbiting close to one of these stars. Now, you might be wondering, how can these relatively small, dim, and unpredictable stars be important? Well, it's not just their oddity that makes them interesting. Red dwarfs hold a vital place in the search for exoplanets, planets that orbit stars outside our solar system. In fact, many of the exoplanets that astronomers have discovered so far are orbiting red dwarfs. And why? Because red dwarfs are so common and so long-lived. These stars provide a stable home for planets to form and evolve, and they can continue to support life for much longer than planets around hotter stars. For the search for extraterrestrial life, red dwarfs are an ideal target. Even though red dwarfs are smaller than our sun, they can have a significant impact on the planets in their orbits. If a planet is too close to a red dwarf, it might get blasted by the star's intense flares, making life, as we know it, almost impossible. However, if the planet is at just the right distance, not too close but not too far, it might have the right conditions for liquid water to exist on its surface, and that, of course, is key for life. This balance is why red dwarfs play such a crucial role in the hunt for habitable planets. They may be small, dim, and somewhat temperamental, but they could hold the key to discovering life beyond Earth. So, red dwarfs are truly unique. They're the quiet workhorses of the galaxy, stable, long-lived, and full of mysteries. Their small size and cool temperatures make them very different from our own sun, and yet they dominate the stellar population of the Milky Way. And while they might not be as flashy or dramatic as the bigger, hotter stars out there, they've got their own story to tell, one that's still unfolding. But as important as they are to our understanding of the universe, red dwarfs still hold many secrets. We've only just begun to scratch the surface of what makes them tick, and as our technology improves, we may find that these humble stars are hiding far more than we can imagine. Before we dive deeper into what Wolf 359 can teach us about red dwarfs, It's worth considering one more thing about these stars: their incredible resilience. In a universe that's constantly changing, red dwarfs represent a type of cosmic endurance that's unmatched. They are the stars that could survive long after the lights of other, more dramatic stars have dimmed, lighting the way to a future we're only beginning to understand. So, with that in mind, let's return to Wolf 359, one of the closest and certainly the most interesting red dwarfs we know of. How does this tiny star stack up against the peculiar traits we've just uncovered about red dwarfs? Let's find out. Imagine, if you will, a tiny, faint star quietly drifting through space, just 7.9 light-years away from Earth. Now, you might think, that's pretty close. Surely we should be able to see it with our naked eyes, right? Well, not exactly. Despite its proximity, Wolf 359 is completely invisible to the human eye. In fact, it's so faint that you could be standing in a field on a clear night, staring up at the sky, and you wouldn't even know it was there. Why is that? Well, Wolf 359 has a luminosity so dim that its apparent brightness, or magnitude, is 113.5. To give you some context, stars like the ones we see twinkling above us, such as Sirius, the brightest star in our night sky, have an apparent magnitude of 1.5. The lower the number, the brighter the star. So, with a magnitude as faint as 113.5, Wolf 359 is not the sort of star that lights up the night sky. In fact, it's so faint that even the most experienced astronomers, without the right equipment, would be hard-pressed to pick it out. But despite its invisibility, Wolf 359 is incredibly important, and its faint glow hides a fascinating story. Discovered in 1917 by German astronomer Max Wolf, who was using photographic plates to scan the night sky, this star became a key part of our understanding of the universe's stellar inhabitants. Wolf's careful work revealed this tiny red dwarf, and its discovery was the start of a journey to uncover the quiet role these stars play in our galaxy. It's hard to believe that, all these years later, this almost invisible speck of light would become one of the most intriguing stars on our celestial map. So, how do we see it today? Well, you won't be spotting it with a simple pair of binoculars or even a basic telescope. To observe Wolf 359, you'd need a telescope with a bit more power, something that can pull in the light from faraway distant stars and bring them into sharp focus. Advanced equipment like modern observatories with high-resolution imaging or space-based telescopes like Hubble would be your best bet. It's not a star you just stumble upon, but one that reveals itself only to those with the right tools and knowledge. But even with all that technology, what makes Wolf 359 particularly fascinating isn't just its faint glow, it's the way it moves. Despite its dimness, this star is one of the fastest-moving stars in our sky. It has what's known as proper motion, a term that refers to the star's movement relative to the background stars in the sky. In fact, Wolf 359 is shifting across the heavens at a staggering rate. If you could sit and watch it over time, you'd notice it streaking across the sky, making it a true cosmic wanderer. While most stars seem to stay more or less in the same relative position to one another, Wolf 359 is constantly on the move. It's almost as though the star is trying to escape the vastness of space itself. Now, this motion isn't just happening now, it's something that's been going on for quite some time. In fact, Wolf 359's rapid movement means it's not going to stay where it is forever. It's traveling through space, and, in the distant future, it could even get closer to Earth. But by the time that happens, it'll be far beyond our lifetime. It's a reminder that even though we think of the stars as being fixed in place, they are in constant motion, drifting through the vast emptiness of the cosmos. Nothing in space stands still. As much as we might try to map out the stars in fixed patterns, they're always on the move, making the night sky a constantly shifting canvas. But let's pause for a moment and think about what Wolf 359's position and motion mean. Despite being so close in cosmic terms, it's invisible to us because of its lack of brightness. It's a bit like a whisper in the vast, noisy crowd of the cosmos. This star, in all its quietness, serves as a metaphor for humility on a cosmic scale. In a universe full of dramatic supernovae, dazzling nebulae, and massive stars, Wolf 359 is an almost unnoticed, humble neighbor. It's easy to get lost in the awe of the more flamboyant parts of the universe, the stars that burn brightly, explode into life, and dominate the sky. But Wolf 359 reminds us that not everything in the universe seeks attention. Some stars, like this one, are content to just quietly exist, going about their business, barely noticed by the humans below. This sense of cosmic humility is what makes Wolf 359 so intriguing. It's a star that's right next door in the grand scheme of things, and yet it remains hidden in plain sight. Its dim light, while fascinating, doesn't demand our attention. Instead, it invites us to think about the nature of the universe, a place full of wonders that we might not always notice, but that can reveal themselves when we look closely enough. It's a reminder that, for all our curiosity, there's so much more out there that we haven't yet discovered or perhaps even understood. And yet, as Wolf 359 drifts quietly through the galaxy, it isn't just another faint star. It's a key player in the story of red dwarfs, those long-lived, slow-burning stars that are quietly filling the universe. While we've spent most of our time focusing on the more dramatic stars, it's the Wolf 359s of the universe that are slowly, steadily, becoming more important in our search for exoplanets, life beyond Earth, and a deeper understanding of what the cosmos really holds. So, while you may never see Wolf 359 with the naked eye, its story is far from over. It's out there, moving across the sky, a quiet reminder that sometimes the most important things are the ones we least expect. In the next section, we'll dive into why red dwarfs like Wolf 359 are so significant in our hunt for life beyond Earth. Even if we can't see them, they could very well be the key to understanding the future of the universe, and possibly even our place within it. Imagine you're watching a classic sci-fi series, and a battle unfolds in the depths of space, amid the vastness of the universe. Ships are zooming past planets, lasers are blasting, and a dramatic backdrop sets the stage for a pivotal moment. Suddenly, you're hit with a location, a name, Wolf 359. For many fans of Star Trek, this isn't just a random celestial body, it's one of the most iconic star systems in science fiction. The Battle of Wolf 359, as it's known, is a central event in Star Trek. The Next Generation, specifically in the two-part episode, The Best of Both Worlds. This battle marks a critical moment in the Star Trek universe where the Federation's fleet fights the Borg, an enemy race that assimilates entire civilizations. The location of the battle? The Wolf 359 star system. While this was a fictional use of a real star, the choice wasn't arbitrary. Wolf 359 became a symbolic backdrop for the devastation, a marker of a major turning point in the Star Trek narrative. The name of the star immediately conjures images of a distant, nearly invisible point of light in the vastness of space. Yet in this context, it's a significant marker of something much larger, a struggle for survival and the uncertainty of facing an unstoppable force. Now, you might be wondering why sci-fi creators are so drawn to using real star names like Wolf 359. Why not invent some obscure, made-up star for these high-stakes, futuristic narratives? Well, the truth is, real stars, with their rich histories and mysterious qualities, add a layer of authenticity to the stories. When writers use actual celestial bodies as a backdrop for spacefaring adventures, it grounds the story in something tangible. It brings the vast, unknown universe a little closer to reality. After all, the universe is real, even if the stories we tell about it are fictional. And in a genre built on wonder, intrigue, and curiosity, Science fiction often mirrors our own attempts to understand the cosmos. By referencing real stars like Wolf 359, science fiction helps spark our imagination, pushing the boundaries of what we think is possible while connecting us to the reality of our world and the stars that surround it. Beyond Star Trek, Wolf 359 has popped up in a few other places in the world of fiction. Its name appears in books, movies, and even video games, often as a distant, enigmatic point of reference, evoking the same sense of cosmic mystery. For example, in the Expanse series by James S.A. Corey, a similar tone of isolation and importance can be felt when characters look to the stars. While they don't specifically mention Wolf 359, the themes of navigating a universe filled with distant stars, unexplored planets, and the ever-present danger of the unknown echo the very essence of the red dwarf system. But it's not just Star Trek or The Expanse that have latched onto the idea of Wolf 359. The idea of a red dwarf star, like the one Wolf 359 represents, has made its way into several science fiction stories. In these narratives, red dwarfs are often portrayed as ancient, dying stars. They could be the remnants of a once vibrant cosmic neighborhood, now on the edge of a long, slow burn toward oblivion. Other times, red dwarfs take on a more ominous role, perhaps as a source of radiation or erratic solar flares that threaten surrounding planets. These fictional depictions offer a blend of the familiar and the unknown, taking real scientific principles about red dwarfs and building on them for dramatic effect. In these stories, red dwarfs aren't just stars. They are symbols of forgotten eras, post-apocalyptic suns, or strange cosmic forces that could bring both life and death to planets in their vicinity. But beyond their use in storytelling, there's something else about these stars that has drawn the attention of scientists and fiction writers alike: their longevity. Red dwarfs like Wolf 359 burn their hydrogen so slowly that they can live for trillions of years. This lifespan gives them a sense of permanence in the universe, a reliability that other stars, like our Sun, simply don't have. In science fiction, this long life can be a double-edged sword. While red dwarfs might be seen as stable, they can also become sources of mystery and danger. If one were to approach a red dwarf, it would likely appear as a dim, almost indiscernible dot in the sky, its glow faint compared to the more luminous giants we know so well. Yet, the longer these stars exist, the more potential they have to play host to planets with complex ecosystems or even civilizations. The way Earth could have one day been cradled by a long-lived red dwarf. It's this juxtaposition of stability and danger that makes red dwarfs like Wolf 359 so appealing in both scientific circles and science fiction. These stars are perfect metaphors for the balance between what we know and what we don't, the familiar and the alien. They exist in a twilight zone of cosmic life, not quite the massive, short-lived giants like blue supergiants, and not the explosive, violent death throes of stars like our own Sun when it eventually dies. Red dwarfs are the quiet, enduring fixtures in the night sky, steady and persistent, even as the universe around them changes. This theme of longevity is especially resonant when we think about how science fiction often portrays red dwarfs as the homes of ancient civilizations. In some stories, entire cultures have lived on planets orbiting red dwarfs for billions of years, their societies surviving long after the stars around them have burned out. These stars become the anchors of cosmic history, holding ancient stories within their faint light. But of course, this idea of ancient stars is not entirely fictional. In our universe, red dwarfs like Wolf 359 could very well host planets that harbor life, potentially making them prime candidates for the search for exoplanets and alien life. That brings us to a thought-provoking question. Could some of the fictional portrayals of red dwarfs and their planets ever become reality? Could we one day discover a thriving civilization orbiting a star like Wolf 359? Could life, in some form, exist in such distant, dim places? The answer, as science fiction likes to remind us, is that we can never really be sure until we venture out and look. In a way, fiction and science are two sides of the same coin. Science fiction inspires the scientific curiosity that leads to real-world exploration, and discoveries in the field of astronomy feed the imagination that brings these fictional worlds to life. Looking ahead, Wolf 359 could hold even more significance in future space exploration. As technology advances and our telescopes become more powerful, we may eventually be able to study red dwarf systems in greater detail. Perhaps one day we'll find a planet orbiting a star like Wolf 359 that could support life, or we may encounter phenomena around these stars that even the most imaginative sci-fi writers haven't yet predicted. The fascinating part of the Wolf 359 story is that we're only just beginning to scratch the surface, both in terms of scientific knowledge and its role in popular culture. And who knows? Perhaps a new generation of storytellers will once again look to Wolf 359, drawing inspiration from this quiet, distant red dwarf and weaving it into their own visions of the future. Just as the battle at Wolf 359 became a pivotal moment in Star Trek, maybe one day this star will play a starring role in the real-life exploration of the cosmos. For now, though, it remains out there in the dark, inviting us to dream, question, and explore the mysteries of space. So, as we wrap up this exploration of Wolf 359 in fiction and culture, we can't help but wonder, what other stars, hidden in the vastness of the universe, are waiting to inspire us in ways we haven't even imagined yet? What stories lie in the quiet, unassuming points of light above us, just waiting for us to notice them? And, most intriguingly, what will we discover when we finally go looking? As we move forward in our quest to understand the stars, the next chapter of Wolf 359's story is still unfolding. There's something inherently dramatic about the idea of a star swallowing a planet whole. It's a narrative that makes for a great science fiction plot, right? After all, what could be more apocalyptic than the thought of a fiery star engulfing everything in its path, including Earth? So when we think about Wolf 359, this tiny red dwarf star that sits just 7.8 light-years away, it's easy to picture it looming over our planet, taking us into its gravitational grip like a cosmic predator. But could it really destroy Earth? Could Wolf 359, despite its size, ever swallow our planet? Let's first take a moment to debunk this dramatic image. No, Wolf 359 isn't going to gobble up Earth anytime soon. You can breathe easy. To understand why, we need to zoom out and look at how stars interact with planets and their environments. Stars, even ones like Wolf 359, don't just eat planets by some force of cosmic appetite. But what if it could? What would need to happen for Wolf 359 to have any kind of significant impact on Earth? In most cases, for a star to pose any serious threat to our planet, it would have to get dangerously close to us. So what's the likelihood of Wolf 359 or any star making such a move? Let's think about it this way. The Sun, our own life-giving star, is approximately 109 times the diameter of Earth. Now, Wolf 359? It's tiny in comparison, only about 1/7 the size of the Sun. So, could it grow large enough to actually swallow Earth? Not really. Wolf 359 is a red dwarf, which means it burns at a much lower temperature than our Sun and is far dimmer. If it were to somehow expand to the size of a red giant, it might theoretically stretch its outer edges into the solar system, but it's not even close to that stage yet. In fact, this type of star has a very long, slow life cycle, so we're talking billions of years before any such scenario could even begin to take shape. Still, let's entertain the idea. What would happen if, hypothetically, Wolf 359 somehow moved closer to us? Even in this far-fetched scenario, there's a lot that would have to align in very specific ways for any real harm to come our way. For one, stars don't usually just wander into other solar systems. They move along their own path in the Milky Way, and the distances between them are vast. Wolf 359, as we mentioned, is already 7.8 light-years away. That's incredibly far, especially when you think about how fast stars move through space. Even if it did somehow come close, the gravitational disruption it would cause would be minimal compared to the Sun's constant influence on the Earth. Now, let's shift gears a little bit and think about what might happen if something were to throw our peaceful cosmic neighborhood into chaos. Imagine a rogue star, one that's not in a fixed orbit and could possibly enter our solar system. Rogue stars, as you might guess, are incredibly rare, but they are real. Take Schultz's star, for instance. This star passed within about 52,000 light-years of our solar system about 70,000 years ago. While it's not exactly close, the gravitational effects it might have had on the Oort cloud, a vast region of icy bodies on the edge of the solar system, could have potentially disturbed comets and sent some on collision courses with the inner planets. If something like that happened with Wolf 359, the gravitational effects would still be significant, but more on a cosmic scale than something that would actually swallow Earth. The more likely danger would come from the disruption of distant objects in our solar system, particularly in the Oort cloud, which is full of icy comets. A rogue star could send one of these comets flying inward toward the inner planets, triggering a collision or a series of impacts that could disrupt life on Earth. While that sounds catastrophic, the probability of such an event occurring in the next few billion years is extremely low. So, let's take a step back from the dramatic imagery of stars devouring planets and instead focus on the real risks that stars like Wolf 359 could pose. When we look at red dwarfs specifically, there are certain threats we need to consider, not from their size or proximity, but from their activity. Red dwarfs are known for being active little stars with flare storms and radiation bursts. These events happen when a red dwarf releases large amounts of energy in the form of flares. The radiation from such flares could potentially disrupt the atmospheres of planets orbiting close to them. Now, this doesn't mean that Wolf 359 is actively sending out dangerous flares toward us right now. That would require a level of direct interaction that we're simply not dealing with at this moment. But if we lived on a planet orbiting Wolf 359, the constant barrage of flare activity could be a serious issue. The radiation emitted by these flares can strip away atmospheres, cook any potential life on a planet, and generally wreak havoc on a fragile ecosystem. This is particularly true for planets that are closer to the star, where the radiation is more intense. Earth, of course, is far enough from Wolf 359 that we don't need to worry about this kind of radiation disrupting life here. But let's take this one step further. Can stars ever really eat planets? Stars, in the way we typically imagine them consuming something, don't actually eat planets in the sense of engulfing them whole. What does happen, though, is that when stars end their life cycles, they can expand and take out anything in their immediate vicinity. For example, our own sun will eventually expand into a red giant, which will likely engulf the inner planets, including Mercury, Venus, and possibly Earth. This process, known as stellar evolution, is inevitable for stars like ours. But it's important to note that this is a natural part of the life cycle of stars, and it's something that happens over billions of years. It's not a violent, sudden swallowing, but a slow, gradual process. So, what does this tell us about Wolf 359? Will it ever swallow anything? Well, considering its current size and its place in the universe, Wolf 359 will likely remain relatively stable for billions of years to come. However, in the distant future, as stars evolve and the universe continues to change, we might witness new dynamics and interactions. If Wolf 359 were to somehow explode in a supernova or go through some dramatic stellar change, it could send out waves of radiation and particles that would affect nearby celestial bodies. But for now, it's not a star that's actively on a collision course with Earth. So, we've explored a few what-if scenarios, but let's finish with a reality check. While stars like Wolf 359 aren't going to consume Earth, we do have to be mindful of the real cosmic threats. There are examples in our own galactic backyard of stars that could come closer to us in the future, like Gliese 710. This star is predicted to pass within 1.3 light-years of the Sun in about 1.3 million years. While this won't lead to any catastrophic collisions, it could certainly disrupt the Oort cloud, sending icy objects toward our solar system and maybe even altering the orbits of planets. It's a reminder that while the universe is mostly peaceful, there are always possibilities for surprises. As we move forward in this exploration, it's worth keeping in mind that stars, like the mysterious Wolf 359, might not be the immediate threats we sometimes imagine. But they do provoke important questions about the future of our planet, our place in the cosmos, and the forces of nature that shape the universe. So while we're not in any immediate danger of Wolf 359 eating us alive, it's always fascinating to look up at the stars and wonder, what's really out there waiting to surprise us? As we venture deeper into the cosmic realm, there's a fascinating idea that keeps coming up. Could there be life around a red dwarf star like Wolf 359? It's a thought that sparks the imagination. After all, red dwarfs are the most common type of star in the universe. In fact, roughly 70% of the stars in our galaxy are red dwarfs. With such a dominant presence, the possibility of habitable planets orbiting these stars is not just intriguing, it's almost inevitable. But what would life on such planets look like? Could anything truly thrive around a red dwarf, especially one as unique as Wolf 359? First, let's take a look at what habitable means in this context. When scientists talk about the habitable zone, they're referring to the region around a star where conditions are just right for liquid water to exist, a crucial ingredient for life as we know it. Now, here's the catch with red dwarfs. Their habitable zones are much closer to the star compared to our Sun. Since red dwarfs are smaller and cooler, their habitable zone exists much closer to them, potentially making the planets in these zones far more vulnerable to other types of dangers. For example, imagine a planet orbiting a red dwarf star, right in the sweet spot where water could exist as a liquid. Sounds perfect, right? But there's a hidden twist. Because the planet is so close to its star, it could become tidally locked. This means one side of the planet always faces the star, while the other side remains in perpetual darkness. On the star-facing side, temperatures could rise to scorching levels, making it a molten, boiling wasteland. Meanwhile, the dark side would be locked in an eternal frozen night, potentially colder than any place on Earth. This makes life, as we know it, very unlikely on either side, unless it's somehow adapted to these extremes. But let's entertain the idea for a moment. What if life could adapt to these conditions? After all, life on Earth has proven time and time again that it's adaptable. From the deepest ocean trenches to the driest deserts, life finds a way. So, maybe, just maybe, some form of life could evolve on the twilight zone, the narrow strip between the hot and cold sides of a tidally locked planet. This strip, called the Terminator Line, would experience a more temperate climate and could offer just the right conditions for life to thrive, if it could handle the constant tug of radiation and the challenges of a relatively small habitable zone. But here's another twist. Red dwarfs aren't exactly known for their calm, predictable behavior. In fact, they tend to have flare storms, intense bursts of radiation that can wreak havoc on anything living on planets around them. Wolf 359 itself is no exception. These flares can strip away atmospheres, heat up surface waters, and potentially endanger any form of life trying to get a foothold. The frequency and intensity of these flares could vary, but life on a planet orbiting such a star would need to be exceptionally resilient to survive constant bombardment. In a world like this, biological adaptations would need to be extraordinary. Imagine organisms that could withstand constant radiation, perhaps developing tough, reflective surfaces to shield themselves. They could possess unique biochemical pathways that allow them to repair their DNA quickly, much like how certain bacteria on Earth can survive radiation levels that would kill other life forms. Life on a tidally locked planet around a red dwarf might not look anything like the plants and animals we're used to, but it could certainly be strange and alien in ways we can't yet fully comprehend. Now, let's step back for a second and think about the kind of planets we could expect in the vicinity of red dwarfs. Given the proximity of their habitable zones, we could see rocky planets, similar to Earth, or perhaps water worlds, a planet completely covered by oceans with no land in sight. Planets like this could have extensive marine ecosystems, with life evolving in ways that depend entirely on the ocean's depths and the planet's unique conditions. Take, for example, the TRAPPIST-1 system, a group of 7 Earth-sized planets orbiting a red dwarf star located about 40 light-years away. Some of these planets sit right in the habitable zone, offering the potential for liquid water to exist. Even more tantalizing is Proxima Centauri b, which orbits the closest star to Earth, Proxima Centauri, a red dwarf as well. It's within the habitable zone of its star, which has sparked a lot of excitement among astronomers and scientists. However, the constant stellar activity from these stars means that the planets may face a daily battle against radiation. But could life still evolve on these worlds, adapting to the harsh conditions? It's an exciting question to consider. If life could evolve in these hostile environments, what would it look like? Picture it. Organisms that might not rely on sunlight the way we do. Instead, they could thrive in the deep oceans, powered by geothermal energy from the planet's core, or even chemical reactions instead of photosynthesis. These life forms could be based on entirely different biochemistry, perhaps utilizing elements or compounds we wouldn't expect. For instance, in place of carbon-based molecules, life might form using silicon, or some other exotic chemistry we haven't even begun to fully explore. Xenobiology, the study of alien life, could be completely redefined if such organisms existed. But we're not just talking about the potential for microbial life here. What if more advanced forms of life, capable of complex thought and intelligence, evolved under these extreme conditions? It's a mind-boggling thought, especially when considering how such beings would adapt to life under constant stellar radiation, with little protection from their parent star. Would they develop thick, radiation-resistant exoskeletons? Could they live underground to avoid the worst of the radiation, creating whole subterranean ecosystems? The possibilities are endless. And here's something even more intriguing. Imagine if intelligent beings living in these extreme conditions developed a completely different way of perceiving their environment. Without a stable day-night cycle, their sense of time could be radically different from ours. Their communication methods might be based on chemical signals rather than sound. The way they structure their societies and interact with each other could be unlike anything we've ever seen. Life in the twilight zone of a tidally locked planet would likely be as bizarre and alien as we can imagine. So, what does all this tell us about life around red dwarfs? Despite the harsh conditions, it's not entirely out of the realm of possibility that life could exist around stars like Wolf 359. However, it would likely be far different from what we know, shaped by the unique challenges of living in the constant glow of a red dwarf. Whether it's microbial life hiding in the oceans of a water world or more complex organisms in the twilight zone of a tidally locked planet, the potential for life is there, just waiting to be discovered. This brings us to an interesting question. Could such life ever make contact with us? Or are we simply too far apart, living in different corners of the universe, each in our own tiny bubble of existence? If you've ever looked up at the sky and marveled at the warm golden glow of the sun, you've probably never given much thought to what life would be like under a different star. But imagine, for a moment, that Earth wasn't orbiting our familiar yellow star. What if instead we were circling a red dwarf like Wolf 359? How different would our world be? Would life as we know it even exist? To truly understand the impact of this question, let's start with a comparison between our Sun and the red dwarf stars that are so common in the universe. The Sun is a G-type main sequence star, which, in simple terms, means it's a middle-aged, stable powerhouse. It's a relatively normal star in the grand scheme of things, neither too hot nor too cold, neither too big nor too small. Its stability has allowed life on Earth to flourish for billions of years. But red dwarfs, like the one lurking at the heart of Wolf 359, are a completely different story. Red dwarfs are smaller, cooler, and far less luminous than the Sun. In fact, they only shine with a fraction of the Sun's energy, yet they are some of the oldest and most numerous stars in the galaxy. There are estimates that nearly 70% of all the stars in our Milky Way are red dwarfs. So, while our Sun might be the star that nourishes Earth, red dwarfs are the celestial neighbors that dominate the stellar population. But just because they're common doesn't mean they're better. At least, not for life as we know it. One of the most fascinating aspects of red dwarfs is their incredible longevity. While our Sun has a relatively short lifespan of about 10 billion years, around 4.6 billion of which have already passed, red dwarfs can live for tens to hundreds of billions of years. This makes them the tortoises of the stellar world, slow-burn stars with the potential to last far longer than our Sun ever will. But here's the catch. While red dwarfs may live longer, they also burn much more slowly. The Sun's energy output comes from a process known as nuclear fusion, where hydrogen atoms fuse to form helium, releasing vast amounts of energy. This process in red dwarfs happens at a much slower rate, meaning their energy is less intense. For any life that might exist around a red dwarf, this slow and steady burn could be a double-edged sword. The trade-off between a star's longevity and its energy output has a profound effect on the planets that orbit it. With a red dwarf's weaker energy, the habitable zone, the region where conditions are just right for liquid water to exist, would be much closer to the star. Planets in this zone would face an additional challenge. They would likely be tidally locked. This means one side of the planet would always face the star, perpetually baking under its dim red glow, while the other side would be trapped in a cold, eternal night. This condition is much harder for life to adapt to than a planet that experiences the gentle ebb and flow of day and night, like Earth. But the differences between red dwarfs and the Sun don't stop with size and energy output. The flare activity around red dwarfs is something we can't ignore. The Sun, though it does emit solar flares, does so on a relatively stable schedule. These solar outbursts are powerful, but they're usually not constant enough to pose a significant threat to life on Earth, especially since our atmosphere and magnetic field protect us. In contrast, red dwarfs are notorious for their frequent and violent flare-ups. These stars can produce massive bursts of radiation, much stronger and more frequent than the occasional solar flares we see from our Sun. For a planet orbiting a red dwarf, this could spell disaster. Constant bombardment from radiation could strip away a planet's atmosphere, scorch its surface, and wipe out any emerging life forms before they have a chance to evolve. Life, if it were to exist around a red dwarf, would have to be exceptionally hardy to survive in such a harsh environment. Now, let's talk about photosynthesis, something we often take for granted on Earth. On our planet, plants use sunlight to convert carbon dioxide into oxygen and glucose, providing food for nearly every living creature. But on a red dwarf planet, where sunlight is weaker and much more distant, photosynthesis could become a challenge. Life that relies on photosynthesis would have to deal with much less energy to fuel its processes. Could plants evolve to use the dimmer red light in a different way, perhaps even tapping into other forms of energy like geothermal heat? Or would life have to adapt entirely different ways to generate energy, maybe through chemical processes instead of relying on light? This is a key point to think about. Planets orbiting red dwarfs might have the right conditions for life to start: water, the right chemicals, and enough time for evolution. but the weak sunlight could hinder the development of complex life as we know it. While simpler organisms might thrive in the oceans, the evolutionary leap to photosynthetic life and beyond might be far harder to achieve. So, is Earth simply lucky to orbit a G-type star? In many ways, yes. The Sun's energy output is perfectly tuned to support life. It's not too hot or too cold, and it doesn't subject the planet to dangerous flare activity that would prevent the evolution of life. Plus, its position in the galaxy places it in a region where conditions are just right for life to emerge, without being too close to the chaos of the galactic core or too far into the cold outer reaches of space. Red dwarfs, on the other hand, present a more complicated story. While they offer a longer lifespan, which could potentially give life more time to evolve, their weaker energy and volatile flare activity make them a challenging home for life. The planets around them would have to endure extreme conditions, with constant radiation exposure and potential tidal locking. Could life adapt to these harsh conditions? Maybe, but it would be a very different kind of life from what we know. So, are planets around red dwarfs more common but less hospitable? In a sense, yes. There's a good chance that most stars in our galaxy are red dwarfs, and many of these stars may have planets within their habitable zones. However, the conditions on those planets are far from ideal for the development of life as we know it. In a way, red dwarf systems may be more common, but the likelihood of finding a truly hospitable planet there is slimmer. As we think about life elsewhere in the universe, we have to ask, are we really as special as we think? If Earth were to orbit a red dwarf instead of a G-type star, would we even be here today? It's a humbling thought. Our planet sits in just the right spot, at just the right time, to allow life to flourish. The sun's steady glow, combined with its relatively quiet nature and the planet's ideal location, has provided the perfect environment for life to thrive for billions of years. This brings us to an important realization. When we look for alien life, we have to consider all the factors that make Earth unique. While red dwarfs may be the most common stars in the galaxy, that doesn't necessarily mean they're the best place to look for life. The conditions they provide, though interesting, are much harsher and less conducive to the kind of evolution that led to humans, plants, and animals on Earth. Imagine a time far beyond our own, a time so distant that it feels like a dream, or maybe a nightmare. 1 trillion years from now, when the bright, fiery stars we see today are nothing but cold, dead embers. Our sun, for example, will have exhausted its fuel, swelling into a red giant before shedding its outer layers and leaving behind a quiet, shrunken remnant. A white dwarf. Most of the massive stars we know and love, like those glowing beacons of light in the night sky, will have burned out, their fuel long gone. But not all stars will meet this same fate. Red dwarfs, on the other hand, will still be here. These tiny, dim stars, so abundant in our galaxy today, will endure long after the larger stars have vanished from the cosmic stage. They'll remain, quietly burning, for tens to hundreds of billions of years. Long after our sun and even the last of its red giant cousins have faded away, red dwarfs will still be shining their faint, steady light across the universe. So, what will the galaxy look like when red dwarfs are the only stars left standing? Let's take a look at this future, a time when the bright constellations of today will be nothing more than distant memories, and red dwarfs will rule the cosmos. In 1 trillion years, the Milky Way will be a very different place. The stars that once dazzled us with their brilliant colors and intense heat will have gone through their life cycles, many of them long gone. The giants, the massive hot stars, will be no more. Instead, what we'll have are red dwarfs. And while they are not the most exciting stars in the galaxy today, in this far-off future, they'll become the dominant presence in the night sky. The galaxy will have a much dimmer, quieter feel to it. The brilliant lights of supernovae will be a thing of the past. Their energetic explosions faded into history. Planets and moons that once orbited bright stars will now circle these cool red giants, bathed in a faint glow. The atmosphere of this galaxy will be different too. Without the intense radiation of the larger stars, the universe will grow darker, quieter, colder. It will be a time of cosmic twilight. Life, as we know it, might be scarce, but the slow-burning red dwarfs will continue their steady existence, providing warmth, albeit a pale, distant warmth, to any surviving planets. These stars could act as cosmic time capsules, preserving the remnants of ancient planetary systems long after their parent stars have passed away. Now, let's venture even farther into the future, into the concept of the heat death of the universe. As the universe continues to expand, it will grow colder and darker. Stars will burn out, and eventually, even the red dwarfs will run out of fuel. But that's still billions, if not trillions, of years away. Red dwarfs, with their incredibly long lifespans, will burn for an almost unimaginable amount of time. As they do, the universe will slowly move toward this state of entropy, a time when all energy is evenly spread out and no more work can be done. This is known as the heat death of the universe. It's a long, slow process, a steady, inexorable march toward cold darkness. The last flickers of light from red dwarfs will be the dying embers of a universe that was once filled with the brilliance of billions of stars. But even in this distant future, red dwarfs won't simply vanish overnight. Their gradual decline into darkness will be a slow and gradual process, and for a while, these stars will continue to burn, faintly but steadily. For any remaining civilizations, they will be the last beacons of hope, the final stars in the universe's long, slow fade. What makes red dwarfs especially interesting in this context is their ability to act as time capsules. Because of their long lifespans, any planets orbiting red dwarfs could potentially survive far longer than planets orbiting larger stars. Imagine a planet that's been orbiting a red dwarf for billions of years. Its surface might be a strange and desolate place by the time the star's light begins to fade. But it would also be one of the oldest planets in the galaxy, holding secrets from a time long past. These planets may still harbor signs of ancient life, frozen in time. Who knows what forms of life could have evolved on planets around red dwarfs? Life might be different, slower, or more resilient than we could ever imagine. Or perhaps these planets might hold nothing but the scars of dead civilizations, preserved in the cold, dim light of their distant stars. In this cosmic future, any remaining intelligent species might be living on these ancient planets, trying to hold on to a dying legacy. They would gaze up at the faint red light of their star, aware that it is all they have left in the darkening universe. Their world, though likely cold and quiet, might still have something to hold on to, something precious. The steady, unchanging glow of a red dwarf star might be their only companion in the deep, endless night. As we look to this distant future, we can't help but wonder, who might still be out there? Could intelligent civilizations persist long enough to witness the era of red dwarfs? It's a tantalizing thought. If life could survive the difficult conditions around a red dwarf, what could that look like? Perhaps, in the far future, there might be civilizations that have evolved to withstand the slow decay of their star. These beings might have long since adapted to their world, finding ways to thrive in the dim light of their red dwarf star. Or perhaps they would be the last survivors, clinging to their worlds as their red dwarf stars fade slowly, gradually. These last civilizations might have developed incredible technologies to survive the heat death of the universe. Maybe they would even look for ways to travel between stars, hoping to find a new red dwarf to orbit, extending their existence just a little longer. It's a thought experiment that feels like something out of science fiction, yet it's based on a future that could one day come to pass. Would these civilizations still remember the brighter days when their stars were larger and their worlds more vibrant? Would they have stories of brighter, more energetic times passed down from generation to generation? Or would they, over time, become so adapted to their environment that they no longer even remember the stars that once lit up their sky? In the end, as the last red dwarf flickers out, the universe will enter a period of complete darkness. But that darkness will not come suddenly. It will be the result of a long, slow decline. For those still around in this era, the end of the red dwarfs will signal the final chapter of a universe that was once filled with light and energy. What can we learn from this future? Perhaps it's a reminder that our time here is limited. The universe, after all, is constantly changing. Stars are born, they live, and they die. And as we gaze up at the stars, we're reminded that our place in this vast cosmos is only temporary. But there's something comforting about the idea of the red dwarfs enduring long after we're gone. They represent the slow, steady march of time, the quiet persistence of the universe as it continues to evolve, even when the brilliance of the stars we know fades away. And in a way, they're a cosmic marker, proof that even in the darkest of times, there's still light, however faint. As we journey deeper into the cosmic mystery of Wolf 359, it's fascinating to think about how much we've learned from this seemingly quiet red dwarf. Despite its modest size and faint glow, Wolf 359 has turned out to be one of the most studied stars in the sky. Scientists have used it to unravel secrets about stellar behavior, the evolution of stars, and even the way our galaxy works. A tiny dot in the night sky, yet a treasure trove of information for astronomers. One of the most intriguing aspects of Wolf 359 is its magnetic field. It's no surprise that stars, even tiny ones like this, have magnetic fields. After all, Earth's magnetic field plays a critical role in protecting us from harmful solar radiation. But Wolf 359's magnetic field is far from ordinary. It's incredibly active, sparking intense flares and storms that can reveal much about how stars like it behave on a smaller scale. Magnetic fields in stars like Wolf 359 are dynamic, constantly changing. This behavior is tied to something called magnetic reconnection, a process where magnetic field lines from different parts of a star suddenly snap and reconnect, releasing vast amounts of energy. It's this process that causes the flares we see on stars like Wolf 359, events that are far more frequent and intense than those we experience on the Sun. What does this mean for scientists? Well, by studying the magnetic reconnection events on Wolf 359, astronomers can gain deeper insights into how stars generate and sustain these powerful magnetic fields. It also helps them understand the interactions between stars and their surrounding environments. With a star like Wolf 359, researchers are better able to predict the behavior of other low-mass stars in our galaxy, which could ultimately affect our understanding of stellar atmospheres and the space weather around other stars. When it comes to studying stellar evolution, the way stars are born, live, and eventually die, Wolf 359 holds a special place. As a low-mass red dwarf, it provides astronomers with a perfect laboratory for studying the life cycle of stars that don't burn out quickly. In fact, red dwarfs like Wolf 359 are some of the oldest stars in the galaxy and can live for trillions of years, long outlasting the Sun and other more massive stars. This means that studying them is crucial for understanding not just the current state of our universe, but also its far-off future. The longevity of red dwarfs like Wolf 359 presents an interesting challenge to stellar evolution models. These stars don't follow the typical patterns seen in more massive stars. For example, red dwarfs spend most of their lives in a quiet, stable phase known as the main sequence, where they burn hydrogen into helium, but at a much slower rate than larger stars. This slower pace means that red dwarfs don't go through dramatic phases of stellar expansion, collapse, or supernova explosions. Instead, they quietly burn away for an incredibly long time. By studying Wolf 359, astrophysicists are able to refine their models of stellar evolution, particularly for low-mass stars. These models help explain how stars like it can persist for so long and what might eventually happen when they run out of fuel. Wolf 359's behavior is a key piece of the puzzle, allowing scientists to predict the fate of many other stars that might share similar traits. But how do we actually see what's happening on a star like Wolf 359? How do astronomers peer into the depths of its fiery core from millions of light years away? The answer lies in spectroscopy, a technique that allows scientists to break down the light coming from a star into its component colors, much like a prism separating light into a rainbow. When we observe the light from Wolf 359 through a spectrometer, we see specific patterns and absorption lines that tell us what elements are present in its atmosphere. This is how we know that Wolf 359 is composed mainly of hydrogen and helium, with traces of heavier elements like carbon and oxygen. These elements are crucial for understanding the star's internal structure and the type of nuclear reactions occurring in its core. These spectroscopic signatures also allow scientists to track the star's temperature, mass, and age. Even though Wolf 359 appears faint to the naked eye, it holds a treasure trove of data that helps astronomers build a clearer picture of what this star is made of, and by extension, how stars like it fit into the broader tapestry of the universe. Red dwarfs like Wolf 359 are critical to understanding the stellar population of our galaxy. Our galaxy, the Milky Way, is made up of billions of stars, but most of them are not like our Sun. In fact, a staggering 70–80% of all stars in the Milky Way are red dwarfs. These stars are the unsung workhorses of the universe, burning quietly in the background, while other, more massive stars grab all the attention. So, what can we learn from these low-mass stars? By studying stars like Wolf 359, scientists can build more accurate models of the galaxy's stellar population. For instance, they can determine the average lifespan of a star in the Milky Way, the types of planets that might orbit red dwarfs, and even the likelihood of life existing around these stars. Since red dwarfs are so abundant, understanding their characteristics helps us understand the overall makeup of the Milky Way itself. Wolf 359 plays a crucial role in this research. As one of the closest red dwarfs to Earth, it provides a unique opportunity to study a star that is much smaller and cooler than our Sun, but still plays a fundamental role in the galaxy. It's like peering into the life of a quiet neighbor, one that, despite its reserved nature, is actually a key part of the larger cosmic picture. Looking forward, the study of Wolf 359 and other red dwarfs will only become more exciting. With advancements in telescope technology, astronomers are hoping to observe these stars in new and groundbreaking ways. Instruments like the James Webb Space Telescope will soon provide more detailed infrared observations, which are particularly useful for studying cooler, dimmer stars like Wolf 359. These observations could reveal even more about the star's atmosphere, magnetic field, and behavior, adding new layers of understanding to what we already know. Additionally, as telescopes become more advanced, scientists may be able to directly observe planets that orbit stars like Wolf 359. While Wolf 359 doesn't have any known exoplanets yet, the possibility of finding worlds around such a star is tantalizing. Red dwarfs are considered prime candidates for harboring planets in their habitable zones, regions where liquid water could exist on the surface of a planet, a crucial ingredient for life as we know it. If we find planets around Wolf 359, it could offer a glimpse into a future where life exists in the dim glow of a red dwarf star, far from the light and warmth of the Sun. So, what have we learned from studying Wolf 359? Despite its unassuming presence in the night sky, it has become a key player in the astrophysical world. From its magnetic activity and role in stellar evolution models to its contribution to understanding the composition of stars, Wolf 359 continues to surprise and educate scientists. As we look ahead, we can only imagine the new discoveries that will emerge from our ongoing study of this tiny red dwarf. Imagine standing on a dark, quiet night, gazing up at the stars. Most of them are just tiny pinpricks of light scattered across the vast black canvas of space, calm and unassuming. But what if one of those stars suddenly flared to life, bursting with intense light and radiation that could make even the most brilliant fireworks look like a faint candle? This is the reality of flare stars, and the reason why Wolf 359, despite being so faint and distant, has captivated the curiosity of astronomers for years. Wolf 359 isn't just another red dwarf star, it's a flare star. But what exactly does that mean? Let's break it down. A flare star is a type of star, often a small, low-mass one like Wolf 359, that can suddenly release massive amounts of energy in the form of a stellar flare. These flares aren't like the gentle twinkling you see on a calm night. No, these are violent outbursts of radiation and energy, the kind that can send shockwaves through the surrounding space. So, what's going on behind the scenes that causes these flares, and why are they so important for scientists to study? Flare stars are mostly red dwarfs, like Wolf 359, because these stars have intense magnetic fields and turbulent atmospheres that make them prone to sudden outbursts. Red dwarfs are small, often only a fraction of the size and brightness of stars like our Sun, but they pack a punch when it comes to flare activity. The key to understanding a flare star lies in its magnetic field, a feature that might be hard to imagine but plays a crucial role in its behavior. Magnetic fields in stars, especially flare stars, aren't like the steady, calm fields we see on Earth. Instead, they are turbulent, constantly changing and reconnecting. In stars like Wolf 359, the magnetic field is far more active and chaotic than on a star like the Sun. This creates a sort of magnetic storm in the star's atmosphere, where magnetic loops, known as flux tubes, build up tension. Eventually, this tension is released in explosive bursts, flashes of light and radiation known as stellar flares. These flares are a direct result of the energy built up in the star's magnetic field. When the field lines suddenly snap, they release energy in a burst of high-energy particles and radiation, which is what we observe as a flare. Imagine stretching a rubber band to its limit and then letting it go. The release of energy is similar, only on a much grander scale. The flares that result can be powerful enough to rival the energy of an entire star's surface, even if they only last for a short time. Let's dive a little deeper into the mechanics of these stellar outbursts. To understand the flare's origin, it helps to think of the magnetic field lines as being similar to rubber bands. These field lines twist and tangle in the star's outer layers, where the plasma, a superheated gas made of charged particles, swirls around in a complex dance. As the magnetic lines twist and turn, they build up energy, like a coiled spring. Eventually, the pressure becomes too much, and the magnetic lines snap or reconnect, releasing that built-up energy. This results in a sudden explosion of plasma and radiation, a flare. The energy released during these flares can travel across vast distances, and when we observe them from Earth, we're seeing just a tiny fraction of the total energy that was unleashed in a split second. Now, imagine the size of a flare. Wolf 359, despite being a small star, can produce flares that are thousands of times more powerful than anything we experience on the Sun. This is why studying flare stars like Wolf 359 is so important. It allows astronomers to study the most extreme conditions of stellar behavior and gain insight into how other stars, especially those closer to Earth, might behave. While flare stars might sound like an exciting phenomenon to study, they're not just interesting in a scientific sense. These violent flares can have real consequences, particularly if they're directed toward planets that are close to the star. The radiation and energetic particles released during a flare can be enough to pose a serious threat to nearby planets and their atmospheres. If a planet were too close to a flare star like Wolf 359, it could experience intense radiation spikes that would be dangerous for any potential life. This radiation isn't just limited to light. It's made up of high-energy particles that can damage everything in their path, including the atmospheres of planets. In extreme cases, flares could strip away a planet's atmosphere entirely, leaving it exposed to the harsh conditions of space. But here's the thing. Flares from stars like Wolf 359 aren't always a death sentence for planets. It all depends on the distance between the star and the planet. If a planet orbits too far away, the flare might not be strong enough to have a significant effect. But if it's close enough, the intense radiation could cause serious damage. The real question is whether there are any planets around stars like Wolf 359 that might be close enough to face these risks, but far enough to potentially avoid them. You might be wondering, okay, but isn't the Sun a flare star too? What makes these flares different from the ones we see from our own Sun? It's a good question, and the answer lies in the scale and frequency of the flares. While the Sun does indeed produce flares, they are far less frequent and less intense compared to those of flare stars like Wolf 359. The Sun's flares, although powerful, are usually much smaller in comparison to the eruptions seen on flare stars. Wolf 359, on the other hand, is a constant source of stellar flares. Its magnetic field is much more active, and the flares it produces are often much more intense. The energy released by a single flare from a star like Wolf 359 can be enormous, making it an intriguing subject of study for scientists who want to understand how stars behave under extreme conditions. Furthermore, the Sun's flares are usually confined to the upper layers of the solar atmosphere, while the flares from stars like Wolf 359 can extend far deeper into the star's atmosphere, making them more potent. This difference makes flare stars like Wolf 359 particularly interesting for scientists studying stellar activity, as they provide an example of what happens when a star's magnetic field is in overdrive. Now, let's go back to that thought experiment. Imagine a planet orbiting a flare star like Wolf 359. Could the energy from a powerful flare be enough to strip away the planet's atmosphere and render it completely lifeless? The answer is, it depends. While the flares from stars like Wolf 359 are incredibly powerful, the planet's distance from the star plays a crucial role in determining whether it could survive the intense radiation. If a planet is within the so-called habitable zone, the region where liquid water could exist on its surface, it might be more vulnerable to the effects of flare activity. The radiation from flares could strip away the planet's protective atmosphere, making it inhospitable to life. However, planets that orbit farther away from their parent stars may have a better chance of avoiding this fate, as the energy from the flares would weaken with distance. So, could flares sterilize planets? It's certainly possible, especially for planets in the inner regions of a flare star's habitable zone. But it's not the only factor that would determine the fate of a planet. The type of star, its flare activity, and the planet's distance from the star all play crucial roles in whether or not life could survive. As we move forward in our exploration of the stars, the study of flare stars like Wolf 359 continues to be an exciting frontier. With advancements in technology, scientists are getting better at studying the flares of distant stars, learning not only about the nature of these events, but also about how they affect the planets that orbit them. In the future, as we search for planets that might harbor life, understanding the risks posed by flare stars will be essential. When you think about searching for life beyond our planet, what do you picture? Green, lush worlds, orbiting stars that shine like our sun. Maybe a peaceful, habitable planet, teeming with life and the perfect conditions for civilizations to thrive. But what if I told you that one of the most intriguing places to look for alien life is around a star that's far different from our own? What if life, Even intelligent life could exist around a tiny, faint star like Wolf 359. You might be surprised to learn that, yes, some scientists are betting on it. Red dwarfs like Wolf 359 make up the majority of the stars in our galaxy, and despite being small and unassuming, these stars have sparked quite a bit of curiosity in the search for extraterrestrial intelligence, or SETI, Search for Extraterrestrial Intelligence. You might wonder, though, why look at these faint, distant stars? Can a star like Wolf 359 actually host intelligent life? Well, that's exactly what we're going to explore in this section. So let's dive in. Red dwarfs are the most common type of star in our galaxy, outnumbering stars like our Sun by a large margin. In fact, these stars are so common that they account for about 70–80% of the stars in the Milky Way. But here's the twist. While red dwarfs like Wolf 359 are small, cool, and faint compared to our Sun, they are also long-lived, burning their fuel very slowly. This means they can shine for tens to hundreds of billions of years, far longer than stars like the Sun, which will burn out in just a few billion years. For scientists studying the potential for life elsewhere, this long lifespan is a big deal. A planet that's orbiting a red dwarf star could have more time to develop life, potentially even intelligent life, given the star's steady glow over an extended period. But before we get too excited about the possibility, we need to take a closer look at what life around a red dwarf would actually be like. Could it really thrive? Or would the harsh conditions make it impossible? Let's start with the obvious challenges. A red dwarf like Wolf 359 is cooler than our Sun by a long shot. In fact, it's only about 15% as bright as our Sun. That means any planet orbiting it would need to be much closer to the star to get enough warmth to support life. We're talking dangerously close, perhaps even within the habitable zone, where conditions could allow for liquid water to exist. But this close proximity to the star comes with a few major risks. Remember those flare stars we talked about earlier? Wolf 359 is one of them. That means it's prone to intense bursts of radiation, solar flares, but on a much larger and more frequent scale. For a planet close enough to be in the habitable zone, these flares could be disastrous. Radiation bursts could strip away an atmosphere, sterilizing the planet or making it uninhabitable for any life forms. But let's say we've found a planet in the right spot, one that's far enough away from Wolf 359 to avoid the worst of its flares. Is it still possible for intelligent life to develop there? The answer isn't simple. The planet would need to adapt to a range of extreme conditions, low light, possibly extreme temperatures, and frequent stellar activity. These conditions might shape life in ways we can't easily imagine. Imagine for a moment that life did manage to evolve on a planet orbiting a star like Wolf 359. What might it look like? How could organisms survive in an environment so different from our own? Perhaps they would evolve in ways that we can't even predict, adapting to the dim, reddish glow of the star rather than the bright yellow light we're familiar with. For one thing, any life forms here would need to be incredibly resilient. They would need to adapt to the low levels of light. Instead of photosynthesis driven by sunlight, perhaps these organisms could harness some other form of energy, maybe even chemical energy, or the heat from the planet's core. Their biology would likely be shaped by the harsh environment, a kind of alien life that could look nothing like anything we've encountered on Earth. But here's where it gets even more interesting. Could an intelligent civilization, one with technology and culture, adapt to this environment as well? Consider that any advanced civilization around a red dwarf would likely have to build their technology with the star's instability in mind. Solar flares would be a constant threat, and their communications could be severely impacted by these bursts of radiation. Signals could degrade, radio waves could get scattered, and any long-distance communication might be riddled with interference. Could their tech look different because of these extreme conditions? It's certainly possible. We might imagine that their technology would need to be designed to withstand the constant radiation from their star. Shields to protect their infrastructure from flares, for instance. And their communication methods might be far more advanced than what we're familiar with, relying on technologies that could circumvent the interference caused by solar activity. In a way, their world might be shaped by necessity. They could be the masters of building robust, shielded structures, perhaps even entire underground cities protected from the harsh surface environment. They could have developed ways to communicate over long distances that don't rely on radio waves, perhaps using entirely different frequencies or even laser-based communication that cuts through the noise. If you're familiar with the Fermi paradox, you'll know it's the question that's been keeping scientists awake at night for decades. If the universe is so vast and there are so many potentially habitable planets out there, why haven't we found any evidence of intelligent life yet? The sheer number of stars in our galaxy suggests that intelligent civilizations should be common, yet we've heard nothing from the cosmos. Could red dwarfs like Wolf 359 hold the key to answering this mystery? It's possible. If life does exist around these stars, it might be vastly different from anything we can imagine. These civilizations might be too different to recognize, or perhaps their technology is so advanced that it's beyond our understanding. It's also possible that they've learned to communicate in ways we can't even detect, avoiding traditional radio waves entirely. In fact, it's possible that civilizations around red dwarfs have already faced challenges that we've never considered. Stellar flares, extreme environments, constant radiation. These civilizations could be so focused on survival that they haven't bothered with interstellar communication, or they might be communicating in ways that we can't even detect. But there's another possibility too. Perhaps red dwarfs are just too inhospitable for advanced life to thrive, and we're looking in the wrong places altogether. Maybe, like the Fermi paradox suggests, we're simply missing something. After all, if a civilization can survive and adapt to the extreme conditions around a red dwarf, it might be so alien to us that we wouldn't even recognize it as life. As fascinating as it is to imagine alien civilizations thriving around stars like Wolf 359, there's another big question to consider. How could we ever detect them? With the constant flares and radiation emissions, communication could be a huge challenge. Even if there were a civilization out there, their ability to send signals across the vastness of space would be constantly hindered by the same forces that make their environment so harsh. We already know how difficult it is to send and receive signals through space. Even a small amount of interference can degrade a message. With the interference caused by stellar flares, it's likely that any signals sent from a red dwarf system would be disrupted or lost entirely, making it incredibly difficult to communicate over long distances. So, could we find signs of intelligent life around stars like Wolf 359? The short answer is maybe, but it's complicated. The conditions around these stars make it hard for life to thrive, let alone develop technology and communicate across vast distances. But the sheer number of red dwarfs in our galaxy means that if life can survive and adapt to these conditions, it could be more common than we think. The search for life around red dwarf stars is still in its early stages, and scientists are using new methods to search for exoplanets in these distant systems. As technology advances, we may one day be able to detect signs of life around stars like Wolf 359. And who knows, maybe one day we'll hear a faint signal or catch a glimpse of alien technology, showing us that, even in the most unlikely places, life has found a way to thrive. For now, we continue to wonder. Could there be intelligent civilizations out there, just waiting to be discovered? Or is the universe simply too vast for us to ever fully understand? Only time will tell, but the search continues, and stars like Wolf 359 remain at the heart of the mystery. We often think of stars as fixed points of light in the sky, beautiful and constant, hanging in the heavens like tiny diamonds. But, in reality, stars are always on the move. And when it comes to Wolf 359, one of the closest stars to our own sun, its journey through space is anything but stationary. Imagine standing on Earth and gazing at the night sky. You might see stars twinkling, but they're not static. Each one is hurtling through the vastness of the universe, often at mind-boggling speeds. Some stars, like Wolf 359, may be far from our eyes, but their motion is still shaping the cosmic landscape. So, how exactly do stars move through space? To answer that, we need to look at the larger picture: galactic orbits and gravitational dynamics. The Milky Way, our galaxy, is a massive spiral, and everything within it, our sun, the stars, even vast clouds of gas, moves along a complex and ever-evolving path. It's like being on a cosmic treadmill, but with every step you take, the entire galaxy shifts in a graceful, grand dance. Now, let's zoom in on Wolf 359 itself. This little red dwarf is traveling through our galaxy at an impressive speed. It's moving at about 28 kilometers per second, which might sound fast, but in the vastness of space, that's just a small fraction of what other stars can reach. However, its movement is still significant because it's slowly making its way through the cosmic neighborhood, and its trajectory is taking it through parts of the Milky Way that, in the distant future, might bring it much closer to our own solar system. To give you some perspective, the Sun moves through the galaxy at a speed of around 220 kilometers per second, but it's located much farther from the galactic center. Wolf 359, in comparison, is one of the stars in our stellar neighborhood, and while it's traveling at a fraction of the Sun's speed, it's much closer to us. This is one of the reasons why it's such an interesting object of study. Despite its low speed, its proximity makes it a key player in understanding how stars move in the local galactic region. But how does this motion affect our understanding of star systems? Stars aren't just sitting in one place, they're constantly shifting, sometimes altering their positions relative to other stars. Proper motion, a term astronomers use to describe a star's movement across the sky, is something that's measured over time. For Wolf 359, its proper motion is relatively large, meaning that over a few thousand years, it'll visibly shift in the night sky. While that may not be noticeable on human timescales, it gives scientists important insights into the star's trajectory and its path through space. But what happens if Wolf 359 continues on its current path? Will it come closer to us? Surprisingly, the answer is yes, just not for a long time. Over the next tens of thousands of years, Wolf 359 will continue to move through the galaxy, but its closest approach to our solar system will occur in about 7.8 million years, when it will be just under 7.8 light-years away, still quite far, but closer than its current distance. In the grand scheme of things, that's a blink of an eye. While this isn't an apocalyptic scenario where Wolf 359 will suddenly enter our solar system, it does pose interesting questions. Will Earth feel the effects of Wolf 359's proximity? Probably not. After all, space is vast, and the star will pass through regions that aren't densely packed with planets or other star systems. But imagine for a moment, if humanity has evolved by then, or if we're venturing across the stars ourselves, Wolf 359 might become a target for exploration, as it would be one of the closest stars to Earth. This brings us to the future, the flybys of stars. As Wolf 359 makes its way through the galaxy, it will likely pass by other stars as well. These stellar flybys, though happening over incredibly long timescales, could have interesting implications for the surrounding star systems. A close encounter between stars could disturb the orbits of nearby planets or even trigger gravitational interactions that might cause one star to be ejected from the galactic neighborhood. While these events are rare, they're not impossible, and they play an important role in shaping the structure of the galaxy. To understand the long-term effects of Wolf 359's movement, astronomers use computer simulations that model the future motion of stars within the galaxy. These simulations take into account gravitational forces, stellar interactions, and the way stars move through space. For Wolf 359, these models predict its path through the galaxy over millions of years. It's like watching a cosmic road trip where the destination is still unclear, but the journey itself is full of potential surprises. What makes these simulations fascinating is that they can reveal how the local stellar neighborhood might change over vast periods of time. Will stars in our neighborhood collide or pass by each other? Could Wolf 359 interact with another star, altering its path and speed? The possibilities are endless, and by studying stars like Wolf 359, we can gain valuable insights into the dynamics of the galaxy as a whole. And while these interactions may seem abstract or distant, they're part of what shapes the very fabric of the universe. Just as the motion of one star can influence its neighbors, the movement of entire galaxies can reshape the structure of the cosmos. Our understanding of these movements is constantly evolving, and with each new discovery, we get a clearer picture of how stars like Wolf 359 fit into the larger puzzle of the universe. As we continue to track the motion of stars like Wolf 359, it's important to remember that the journey of any star is not just about its movement. It's also about the relationships it forms with other stars, the forces that shape its path, and the cosmic events that might unfold over eons. While we may never see the dramatic effects of Wolf 359's motion in our lifetimes, the star's story is a reminder of how dynamic and ever-changing our galaxy truly is. Have you ever wondered what it would be like if Earth wasn't orbiting a bright yellow sun, but instead a much smaller, dimmer red dwarf star? What would change about our world? The very idea sparks an array of fascinating questions about how life, the environment, and even our civilization might have evolved differently under the glow of a red dwarf. Let's start with the basics. Red dwarfs are cool compared to our sun. They shine with a soft red light, much dimmer than the brilliant yellow rays we're used to. But that doesn't mean they can't host life. Far from it. In fact, red dwarfs are the most common type of star in the galaxy, accounting for roughly 70–80% of all stars. But while red dwarfs are abundant, they bring a whole new set of conditions that would shape everything from how we live to what we look like. Imagine a world bathed in the red glow of a tiny star. A red dwarf's light isn't just dimmer, it's also cooler, with a surface temperature that's far lower than our sun's. This would make Earth's surface temperature cooler as well. Without the intense heat of our sun, Earth would likely be much colder. Could we still live here? That's the big question. Life might have adapted to the colder climate, but one thing's for sure. Our environment would look vastly different. First, think about the sky. On Earth, we're used to a blue sky during the day, the result of sunlight scattering through the atmosphere. But under a red dwarf, the sky wouldn't be blue. It would be a muted red or orange, bathed in the glow of a constant, weak crimson light. Instead of bright midday skies, it would be like permanent twilight, with a constant warm, red glow hanging over everything. Imagine stepping outside and seeing the world in hues of crimson and amber, the sunlight filtering through the air like a soft, glowing fog. But what about the more important stuff, like how life on Earth would adapt to these new conditions? Well, with less sunlight, plants would have to adapt to make the most out of the dim light. Photosynthesis, the process by which plants convert light into energy, would likely evolve to work with the redder wavelengths of light emitted by the dwarf star. You might picture fields of plants not in the green you're familiar with, but instead shades of black, purple, or deep red. These colors would help plants absorb the right wavelengths of light more effectively. Black plants might be a common sight. After all, darker colors absorb more light. A black forest, rich in life but draped in shadows, would be the new reality. With less energy coming from the sun, the planet's ecosystem would have to find a balance. There might be more energy stored in the soil or from geothermal sources. Plants and animals could have adapted in ways we can't yet predict, perhaps evolving to survive in low light, or even relying on energy from volcanic activity deep within the planet. The idea of a green planet would be replaced by a new palette, one that matches the deep hues of a red dwarf star. Now, let's turn to us, humans. Would we even be able to evolve in such a world? Perhaps. But it's likely that our evolution would be drastically different, shaped by the dimmer light and colder temperatures. Our eyes, for instance, might have evolved differently. Instead of the bright, open-sky vision we have today, perhaps our eyes would be larger or adapted to see better in low-light conditions, similar to how nocturnal animals have better vision in the dark. Humans might even have evolved with different skin tones, perhaps darker skin, to absorb more of the limited light. And what about our lifestyle? Without the regular cycle of sunlight and darkness that drives our circadian rhythm, daily life would feel entirely different. Instead of a predictable day-night cycle, Earth could be locked in a tidal rhythm, where one side of the planet faces the star constantly, while the other remains in perpetual darkness. This phenomenon is called tidal locking, and it happens when a planet's rotation becomes synchronized with its orbit, so one side always faces the star. If Earth were tidally locked to a red dwarf, one half of the planet would be a permanent day zone, while the other half would be in constant night. In such a world, cultures and economies would adapt. Humans living in the perpetual daylight region might develop unique societies, possibly even developing technology to shield themselves from the constant glare. On the night side, civilizations might thrive in the cooler, darker regions, where bioluminescence could light up the landscape in glowing blues, greens, or other strange hues. Imagine a civilization living in perpetual night, where their cities are lit by artificial stars, lights that mimic the distant stars of the sky. What if Earth weren't tidally locked, though? In that case, the day-night cycle would be longer. Instead of 24-hour days, we might have days that last weeks or months. A single day could stretch across the sky, with long, slow sunsets and sunrises that would last for days, perhaps weeks. This kind of slow-moving rhythm would change everything about how we think about time. Imagine the seasons stretching out like long, slow breaths. What would happen to human culture and economies when the concept of a day was so drastically altered? Without a reliable day-night cycle, our internal clocks, our circadian rhythms, would be thrown into chaos. These rhythms guide everything from our sleep patterns to our hormones. In such a world, humans might develop entirely new ways of measuring time, perhaps creating technology to simulate the effects of day and night. Or we might adapt biologically, evolving different sleep cycles to fit the longer, unpredictable days. It's an interesting thought experiment, but one that raises an important question. If we can't even rely on a regular cycle of light and dark, would humans even have evolved at all? Would our bodies have been able to adapt to such an alien world? Now, let's think about how human culture and technology would evolve. If we lived on a planet orbiting a red dwarf, how would our understanding of the world change? Without the traditional seasons, the cycles of spring, summer, fall, and winter, life would look different. Perhaps our celebrations would revolve around the position of the star, marking specific moments in its cycle rather than traditional calendar dates. Festivals might celebrate the moment when the star appears to rise in the sky, even if it's just a gradual, slow change over the course of months. Technology, too, would adapt to these conditions. Energy would be harder to come by, so humans might have developed new methods for harnessing the planet's geothermal energy, or perhaps even tapping into the energy of the star itself, using solar power in ways we can't yet imagine. New technologies might emerge that are specifically designed to deal with the unique challenges of a world with limited sunlight and unpredictable cycles. In a society where the day never truly ends or never truly begins, humanity might adapt in ways we can't predict. But one thing is for sure: it would be a radically different world. Life on a planet orbiting a red dwarf would be alien, not just in the way it looks, but in how it feels. So, what does all this mean for our understanding of life in the universe? Could there be other civilizations out there thriving under the glow of a red dwarf, just as we've thrived under our bright yellow sun? The possibility is exciting. While we've often looked for planets in the habitable zone of stars like our sun, the truth is that life might thrive in places we wouldn't expect. On planets that orbit stars like Wolf 359, those dim, flickering red dwarfs. As we continue our search for life beyond Earth, the question is not just about finding a similar sun, but about recognizing that there may be many different ways life could exist. The universe is vast, and the paths to life are as varied as the stars themselves. As we dream of the stars, perhaps we're only beginning to imagine the many different worlds that might exist under the light of a tiny red dwarf. As we continue our cosmic journey, it's time to take a broader look at the celestial neighbors that make up the family of stars to which Wolf 359 belongs. Imagine you're standing on Earth, looking up at the night sky. You can see the stars that twinkle far away, each one part of a vast and intricate web of stellar systems. But not all of these stars are equal. Some shine brightly, others barely noticeable, and some are small but incredibly important in their own quiet way. Wolf 359 is one of the latter, a red dwarf star, modest in size but mighty in significance. But Wolf 359 doesn't stand alone. It shares its space with other stars that are just as fascinating and, in some cases, even closer to our own solar system. Let's meet this family of stars, these red dwarfs that populate the neighborhood of the galaxy. Wolf 359 is part of a special class of stars known as red dwarfs. These stars are small, cool, and relatively faint, but they're also abundant, making up about 70–80% of the stars in our galaxy. They are, in a sense, the quiet workhorses of the galaxy, outnumbering the bigger, flashier stars like our Sun by a wide margin. One of the most famous neighbors in this red dwarf family is Proxima Centauri, the closest known star to our Sun, located just over 4 light-years away. Proxima is a bit of a celebrity in the astronomy world, mainly because it's so close to us, but also because it has a planet in its habitable zone, potentially offering a glimpse into what alien life might be like on a world around a red dwarf. Proxima Centauri is slightly more active than Wolf 359, with frequent solar flares that make its environment a bit more dynamic. But, like all red dwarfs, it's still faint and quiet compared to our Sun. Then, there's Barnard's star, about 6 light-years away. It's a relatively slow mover in the grand scale of the universe, but still incredibly interesting because it's one of the fastest stars in our region of the galaxy. It might not be as famous as Proxima, but its motion through the galaxy tells a fascinating story about stellar dynamics and the forces at play that send stars speeding through our cosmic neighborhood. Despite its speed, Barnard's star is similarly faint, glowing weakly in the night sky. Lastly, there's Ross 128, a bit farther out at 10.9 light-years away. It's less active than Proxima and even quieter than Wolf 359 in terms of stellar flaring. But it still shares the same characteristics that define red dwarfs, being small, cool, and incredibly stable over the long haul. Like Wolf 359, stars like Ross 128 don't grab headlines in the way that larger, brighter stars do, but they're incredibly important in the context of the universe as a whole. So how does Wolf 359 compare to its neighbors in this stellar family? Well, for starters, Wolf 359 is slightly smaller than many of its red dwarf cousins, and much cooler too. While Proxima Centauri may be more active, throwing out flares and magnetic storms, Wolf 359 is a more subdued star, burning at a steady, calm pace. This makes it less volatile compared to some other nearby red dwarfs, making it a more predictable neighbor in our galactic neighborhood. In terms of size, Wolf 359 is about 1/10 the mass of our Sun, and only about 1/30th as bright. Despite this dimness, it's still quite noticeable to astronomers, especially when you consider how many stars like it are out there. The motion of Wolf 359 is also relatively slow in comparison to stars like Barnard's star, which speeds through our cosmic neighborhood at an impressive clip. While Wolf 359 may not win any races, it's stable, and its predictable motion through the galaxy is part of what makes it so interesting to study. One of the things that makes Wolf 359 and stars like it so compelling is their longevity. Red dwarfs are incredibly efficient at burning their fuel. Unlike bigger stars that burn through their hydrogen quickly and have relatively short lifespans, red dwarfs can live for billions and even trillions of years. This means that while stars like our Sun might eventually burn out in about 5 billion years, red dwarfs like Wolf 359 could continue to shine for tens of trillions of years. This makes them stable, long-lasting beacons in the galaxy, reliable in a way when compared to the short-lived brilliance of more massive stars. Looking at the stars in our local stellar neighborhood, scientists have categorized them based on their characteristics: size, temperature, luminosity, and age. Wolf 359 and its fellow red dwarfs belong to a specific class of stars called M-class stars. These are the coolest, smallest stars in the stellar classification system. Despite their dimness, M-class stars are incredibly numerous. While they may not light up the sky in the same way our Sun does, they make up the majority of stars in the Milky Way. Proxima Centauri, Barnard's star, and Ross 128 also fall into this same category of M-class stars. In the grand scheme of the galaxy, these stars might seem like wallflowers, quiet and understated, but in our local stellar neighborhood, they're the dominant force. In fact, most of the stars that orbit near our Sun belong to this category. When you think of the closest stars to us, many of them are these red dwarfs, shining faintly in the distance. Our Sun, by comparison, is an G-class star, far brighter and more energetic. But it's a member of a much smaller group. When you look at a map of nearby stars, you'll find that the vast majority of stars in our corner of the galaxy are much smaller than our Sun. This is why understanding stars like Wolf 359 is so important. They make up the majority of stars in our cosmic neighborhood, and they have unique characteristics that could make them critical for understanding the future of space exploration. To help make sense of our position in the universe, astronomers use something called a local stellar map. This is essentially a map that shows the stars in the region of the galaxy surrounding us, usually within about 20 light years. When you look at such a map, it becomes clear that the stars closest to us are mostly these dim, distant red dwarfs. These stars don't have the intense luminosity of a star like Alpha Centauri, but they're still close enough to be considered neighbors in the galactic sense. One interesting thing about our local stellar bubble is that we live in a cosmic neighborhood that's dominated by these cooler, smaller stars. As we expand our reach into interstellar space, these stars will become key targets for exploration. In fact, red dwarfs are prime candidates for future interstellar probes. While the concept of sending a probe to another star may sound like science fiction, it's a real goal for future space missions. Proxima Centauri, just a stone's throw away at 4.2 light-years, is already being considered for such missions. As technology improves, we might one day send spacecraft to explore these distant red dwarfs and their planets, looking for signs of life or simply expanding our knowledge of the universe. These stars, with their long lifespans and stable environments, could hold the key to unlocking the mysteries of life beyond Earth. And as we look at the stars like Wolf 359 and its family, we start to see the building blocks of a truly interstellar civilization. The idea of exploring other stars in our neighborhood is an exciting one. While it may take centuries or even millennia for us to develop the technology to reach these distant worlds, the stars in the Wolf 359 family are our closest, most accessible targets. They're the stepping stones to the stars beyond, the first locations we might one day visit as we begin our journey beyond our solar system. Red dwarfs, with their cool, stable conditions, are also great candidates for searching for alien life. Their long lifespans could provide the necessary time for life to evolve on any planets they host, making them perfect places to search for extraterrestrial civilizations. With the discovery of planets in the habitable zone of stars, like Proxima Centauri, these nearby red dwarfs could be home to life that's just waiting to be discovered. Wolf 359 may be small and distant, but it's not alone. It's part of a much larger family of stars that share similar traits, quietly filling the sky with their soft, red light. Together, these red dwarfs make up a vast and largely unexplored portion of our galaxy. As we venture out into the cosmos, stars like Wolf 359 will be the starting points for our journey, our neighbors in the Galactic family that could one day help us unlock the secrets of the universe. So what does this mean for us? It means that the stars closest to us, these dim, unassuming red dwarfs, are key to the future of interstellar exploration. As we look up at the night sky, it's important to remember that our galaxy is full of quiet, fascinating neighbors just waiting to be explored. And perhaps, in the not-so-distant future, one of these stars will be the destination of the first interstellar probe, launching humanity into the greater cosmos. Imagine you're standing on a distant planet, gazing up at the night sky. The stars you see aren't the blazing golden giants like our sun, but instead they're faint, reddish points of light, red dwarfs. These stars might seem small and distant, but in the search for alien worlds, they're like hidden treasure chests. And it's not just their size that makes them intriguing. It's their very nature that makes them some of the most promising places to look for exoplanets, the planets orbiting stars outside of our solar system. Let's take a closer look at why red dwarfs, such as Wolf 359, are so important when it comes to the hunt for exoplanets, and how they could one day help us answer one of humanity's most profound questions. Are we alone in the universe? Red dwarfs are the unsung heroes of the galaxy. Although they're smaller and cooler than stars like our sun, they're also much more abundant, making up around 70% of all stars in the Milky Way. Their sheer numbers make them the perfect target for astronomers in the search for exoplanets. One of the main reasons why red dwarfs are so helpful in this search is due to their smaller size and lower luminosity. A planet that orbits a red dwarf will have to be much closer to the star to receive enough warmth to sustain life, closer than, say, Earth is to our sun. This means that any potential planets in the habitable zone, where liquid water could exist, will be easier to spot because they're closer to their host stars, and this proximity makes it easier to detect their presence. But there's another reason why red dwarfs are so useful in the search for planets, and it has to do with a technique called the transit method. Let's imagine a planet passing in front of its host star. When this happens, the star's light dims just a tiny bit, like a brief flicker of a light bulb. If we're observing that star from a distance, we can detect this dip in brightness and infer the presence of a planet. Since red dwarfs are smaller and cooler than our sun, their light is less intense and more stable, making the planet's transit easier to spot. This makes red dwarfs excellent candidates for finding small, rocky exoplanets, the kind that might have conditions suitable for life. One of the most significant achievements in the search for exoplanets has been the launch of space telescopes like Kepler and, more recently, TESS, Transiting Exoplanet Survey Satellite. These missions have turned the search for planets into something more like a cosmic treasure hunt, with red dwarfs as the gold mines. Kepler's mission was groundbreaking in the way it found thousands of exoplanets, many of which orbit red dwarfs. By focusing on a small patch of the sky, Kepler was able to detect the tiny dips in light from distant stars as planets passed in front of them. Kepler's findings showed that many of the most promising exoplanets, those that might be capable of supporting life, were orbiting red dwarfs. This was exciting news, as it meant that there could be far more habitable planets out there than we'd originally thought. TESS, which launched after Kepler, has continued in the same vein, scanning the sky for stars that might have planets. While TESS has already found hundreds of potential exoplanets, many of its discoveries are around red dwarfs. In fact, about 70% of the stars TESS has observed are M-class red dwarfs. The reason for this is simple. These stars are everywhere, and they're easy to study. With the help of TESS, scientists now have a much better understanding of the prevalence of planets around these stars and what makes a planet potentially habitable. While the search for exoplanets is still in its early stages, scientists have already confirmed several fascinating planets around red dwarfs, and some of them show real potential for habitability. Take Proxima b, for example. It's a planet that orbits Proxima Centauri, the closest star to our Sun, just over 4 light-years away. Proxima b is located in the habitable zone of its star, where conditions might be just right for liquid water to exist. While there are still many unknowns about Proxima b, such as its atmosphere and whether it could support life, the mere fact that it's so close and in the habitable zone is exciting. This discovery suggests that planets like Proxima b could be more common than we ever imagined, orbiting red dwarfs just like Wolf 359. Another example is TRAPPIST-1, a system of 7 Earth-sized planets orbiting an ultra-cool red dwarf star. 3 of these planets are located in the star's habitable zone, meaning they could potentially have liquid water on their surfaces. This makes TRAPPIST-1 one of the most intriguing systems for future study. The fact that all of these planets are relatively close to each other and to their host star makes it easier for astronomers to study them in detail. With the help of advanced telescopes, we could one day learn more about their atmospheres and see if there's any sign of life. Despite the promising possibilities, there are also significant challenges when it comes to studying planets around red dwarfs. One of the biggest challenges is that red dwarfs are known for their stellar flares, violent eruptions of energy that can bathe nearby planets in harmful radiation. These flares are particularly intense in younger red dwarfs, and they can strip away a planet's atmosphere over time, making it less likely for life to develop or survive. This radiation is a major factor that scientists need to consider when studying planets around red dwarfs. Even if a planet is in the habitable zone, its habitability could be compromised if the star it orbits is too active. To make matters more complicated, red dwarfs are known to be tidally locked with their planets, meaning one side of the planet always faces the star, while the other side is in eternal darkness. This creates extreme temperature differences, which could make the planet inhospitable or at least challenging for life to thrive in the way it does on Earth. Another challenge lies in the detection of these exoplanets. While the transit method is great for finding planets that pass in front of their stars, it doesn't work as well for planets that don't align in just the right way. This means that some potentially habitable planets might remain hidden from our current technology. So, what's next in the search for red dwarf planets? The good news is that the hunt is far from over. New space missions and advanced telescopes are being developed to continue the search for planets around red dwarfs and, more importantly, to study them in greater detail. One promising technology is the James Webb Space Telescope, which is designed to study exoplanet atmospheres in unprecedented detail. It could provide us with the first real chance to learn whether any of the red dwarf planets are truly habitable. Another exciting possibility is the development of more advanced space-based interferometers, instruments that could take a snapshot of an exoplanet's atmosphere, searching for biosignatures or signs of life. These missions, if successful, would bring us closer to answering that age-old question: is there life beyond Earth? The search for exoplanets, particularly those around red dwarfs, brings us closer to understanding the broader question of life beyond our solar system. These small, cool stars may seem insignificant at first glance, but in reality, they might be the key to finding alien life. With red dwarfs being so abundant and their planets so numerous, the odds of finding a planet that could support life are looking better every year. As we continue to look toward the stars, the discoveries made around red dwarfs like Wolf 359 could pave the way for future interstellar exploration. Whether we're looking for habitable planets, signs of alien life, or just the next frontier of discovery, red dwarfs offer a vast, untapped treasure trove of cosmic secrets waiting to be uncovered. In the end, the tiny red dwarf that could swallow Earth whole may also hold the answers to some of humanity's biggest questions. And as we venture further into the galaxy, who knows what wonders we'll discover next? The search for life beyond Earth is just beginning, and red dwarfs will be at the heart of that journey. When you think of distant stars like Wolf 359, it's easy to imagine them as unreachable, like glowing dots suspended in the vast, endless canvas of the night sky. But what if, just for a moment, we step away from the usual out-of-reach mindset and entertain the thought? Could we ever visit this tiny, enigmatic red dwarf star? At a distance of 7.9 light-years, Wolf 359 is relatively close by in cosmic terms, just a stone's throw in the grand scale of the universe. But even though it's not the furthest star from Earth, the journey there would still be incredibly daunting. So, let's break it down and explore whether a trip to Wolf 359 is something we could realistically achieve in the future. First, let's try to wrap our heads around just how far Wolf 359 really is. 7.9 light-years. That sounds impressive, but let's bring it into perspective. A light-year is the distance light travels in 1 year, roughly 5.88 trillion miles, or about 9.46 trillion kilometers. So when we say Wolf 359 is 7.9 light-years away, we're talking about a staggering distance of nearly 47 trillion miles, or 76 trillion kilometers. To get there using current spacecraft technology would take thousands, even tens of thousands of years. It's like asking, can we get to the other side of the ocean, when we haven't even learned how to cross the road? But could we, with future technology, shorten that time? That's the million-dollar question. Right now, even the fastest spacecraft humans have ever built wouldn't even come close to reaching Wolf 359 in a single lifetime. The Parker Solar Probe, for example, currently holds the record as the fastest human-made object, traveling at a speed of about 430,000 miles per hour, 700,000 kilometers per hour. That's incredibly fast, faster than anything we've built before. But even with that blazing speed, it would take over 17,000 years to reach Wolf 359. So, as of now, visiting this star is far from practical. But just because we don't have the means to reach Wolf 359 today doesn't mean we won't one day. Scientists and engineers are already thinking about how we could reach stars like it in the future. Let's dive into some of these cutting-edge ideas. One of the most promising ideas comes from Breakthrough Starshot, a project that aims to send small, lightweight spacecraft to nearby stars using the power of light. The plan is to launch tiny star chips, basically little wafers with sensors and cameras attached to light sails, which are large, thin sheets designed to be propelled by light. The idea is that by focusing powerful lasers on these sails, we could accelerate the spacecraft to up to 20% of the speed of light, or about 37,000 miles per second, 60,000 kilometers per second. This is a game changer. At this speed, a spacecraft could reach Proxima Centauri, the closest star to us, in just over 20 years. Reaching Wolf 359 would take a bit longer, but at a fraction of the time it would take with current technology, around 40 years. That's still a far cry from today's space travel times, but it's a significant step forward. Breakthrough Starshot has a lot of obstacles to overcome, like developing the right lasers and ensuring the spacecraft survive the harsh conditions of space, but it's a concept that could someday revolutionize interstellar travel. Now, let's consider a different idea: generation ships. The basic concept behind a generation ship is that it's a self-sustaining spacecraft, built to support human life for many generations. Instead of a quick journey to Wolf 359, it would be more like a slow, ongoing voyage, where the people who leave Earth never see the destination. Instead, their descendants would be the ones to arrive. The challenges here are enormous. For one, a generation ship would need to carry everything required for human survival: food, water, oxygen, and waste management systems for potentially hundreds or even thousands of years. These ships would have to be large and complex, with resources carefully managed. It's a bit like building a floating city that's constantly on the move, forever. But while it's an intriguing idea, generation ships have some major limitations. The technology needed to keep them going for centuries, even millennia, simply doesn't exist today. Not to mention, there are psychological and social factors to consider. How do you keep generations of people motivated with no hope of ever seeing the place they're traveling to? And of course, generation ships wouldn't be very fast. The time it would take to reach Wolf 359, even with the technology we dream of today, would still stretch across hundreds of years. It's not quite a practical vacation spot, is it? Then there's the ultimate dream of near-light speed travel. If we could build spacecraft that could travel at, say, 90% or 99% of the speed of light, the math begins to look much more interesting. At these speeds, a trip to Wolf 359 could take as little as 8 or 10 years. Still quite a long time, but much more reasonable than millennia. But there's a catch. The closer we get to the speed of light, the more complex things become, especially when it comes to time dilation. This is a relativistic effect described by Albert Einstein's theory of relativity. As you approach the speed of light, time begins to slow down relative to someone who's not moving as fast. So, while the astronauts aboard a near-light-speed spacecraft might experience only a few years of travel, those left behind on Earth would experience many more years, possibly decades or centuries, before the travelers returned. This is where the question of, is it worth going there, comes into play. If we can travel close to the speed of light, would we be willing to live through decades of travel, knowing that when we return, everyone we knew on Earth will be long gone? It's a thought-provoking dilemma, and one that's not easy to answer. So, let's pause for a moment and ask, is it even worth going to Wolf 359? Sure, it's an interesting star with a rich scientific background, and its potential planets could be home to alien life. But does that really make it a destination for humans? Right now, the distance alone makes it impractical. With so many other stars and potential planets out there, we have to ask, what's so special about Wolf 359? Could there be closer, more habitable systems? Could the resources we would spend trying to reach Wolf 359 be better spent exploring other parts of our own galaxy, or even finding ways to protect and enhance life here on Earth? Perhaps in the distant future, the motivations for interstellar travel will be clearer. The desire to explore, to learn, to find life elsewhere. These are powerful forces that could push humanity to overcome the unimaginable hurdles of interstellar travel. But for now, it remains a grand idea, one that might only be realized in the distant future. As we step back and think about the possibilities, it's clear that traveling to Wolf 359 is far from a simple endeavor. But that doesn't mean it's impossible. Whether through solar sails, generation ships, or perhaps even faster-than-light travel one day, the dream of reaching another star is alive and well. The road ahead is long, uncertain, and filled with challenges. But in the quest for exploration, that's what makes the journey so exciting. One day, the people of Earth might look up at the stars and know that we didn't just look at them from afar, we reached them. And maybe, just maybe, that little red dwarf star, Wolf 359, will be one of our first stops. Let's say you could fast forward time, not by years or centuries or even millennia, but by trillions of years. The galaxies are dimming. The stars that once lit the cosmos like fireworks are vanishing. Supernovas have long since stopped. Black holes drift silently, slowly evaporating. Everything we know is fading. But out there, still glowing, still stubbornly clinging to existence, is a tiny red star. Wolf 359. It didn't burn fast, it didn't shine bright, but it lasted, quietly, patiently, outliving giants, civilizations, even entire galaxies. So how? How does something so small, so dim, last so long? To answer that, we have to understand one very strange truth about the universe. Sometimes being ordinary is what makes you extraordinary. Most stars live fast and die young. Our sun, it's what scientists call a yellow dwarf, and it's got a respectable life expectancy of about 10 billion years. We're already halfway through that journey. Eventually, it'll swell into a red giant, shed its outer layers, and leave behind a dense little core called a white dwarf. Beautiful in its own way, but very, very dead. But red dwarfs, they're different. These stars are small. Wolf 359 is less than 10% the mass of our sun. It barely puts out any light, just about 0.1% of the sun's brightness. If the sun is a roaring campfire, Wolf 359 is more like a single glowing coal. And yet, in that tiny ember, something miraculous is happening. Because of its low mass and cooler temperature, a red dwarf doesn't just burn slower, it recycles. Unlike larger stars, red dwarfs are fully convective. That means the hydrogen fuel from the outer layers gets stirred around and pulled into the core, where it can be fused. It's like having a pot of soup where the heat stirs everything evenly, keeping it cooking efficiently for an absurdly long time. Result? No waste, no rush, just slow, steady fusion. This little star is in no hurry. And that's exactly why it'll still be shining long after the universe forgets what blue looked like. Let's put this into perspective. Current estimates say a red dwarf like Wolf 359 could live for up to 10 trillion years. That's a 1 followed by 13 zeros. Let that number settle in for a second. That's more than 700 times the current age of the universe. Imagine pressing play at the Big Bang, and then sitting through the entire history of everything we know, galaxies forming, Earth evolving, humans discovering fire and Wi-Fi, and doing that not once, but hundreds of times. And then Wolf 359 is still glowing. Its surface may dim a little, but it just keeps going. Like a cosmic lighthouse, still blinking long after all the ships are gone. Now, red dwarfs like Wolf 359 aren't rare. In fact, they're the most common type of star in the universe. But here's the twist. None of them have died yet. The universe is just 13.8 billion years old, and red dwarfs take trillions of years to burn through their fuel. So every red dwarf that's ever been born is still alive. We've never seen one go out. Think about that. A whole category of star, aging in slow motion, playing the long game. And in the far future, when the last blue giants have flared out, when the white dwarfs have cooled into black chunks of carbon, red dwarfs will be the final stars still glowing. Tiny lights in a very, very dark room. Let's jump ahead. Say, 100 trillion years from now. The Milky Way and Andromeda have long since merged into a new, bloated galaxy, sometimes called Milkdromeda. The night sky no longer sparkles. It glows faintly, like embers in a fireplace that hasn't been stoked in ages. There are no new stars being born, no fresh gas clouds to ignite. The cosmic factories have shut down. Time has slowed to a crawl, and entropy is the only empire that reigns. And yet, Wolf 359 is still there. Old, yes. Dim, probably, but not dead. It's still quietly converting hydrogen to helium, still emitting faint red light, still spinning ever so slowly. A relic of a younger, livelier universe. In a way, Wolf 359 becomes a kind of time capsule, a survivor. Not because it was powerful, or dominant, or flashy, but because it was patient. It simply sipped its fuel while others chugged it like cosmic caffeine. Eventually, even red dwarfs will die. Wolf 359 won't go out with a bang. It'll simply run out of hydrogen. No explosion, no fireworks. It'll fade into a white dwarf and then gradually cool down into a black dwarf, essentially a frozen star radiating no light, no heat. But here's the catch. That final stage may take so long it hasn't even happened anywhere in the universe yet. According to current physics, black dwarfs might not exist yet at all. The universe simply hasn't aged enough to allow even a single red dwarf to burn out completely. Wolf 359 could be one of the last stars in the universe to go dark, a flickering memory of a cosmos that used to shine. There's something hauntingly beautiful about that. We humans are used to the idea of endings. We age, we grow, we fade. Even our solar system is on borrowed time. But stars like Wolf 359 invite us to rethink what long-lived really means. In a cosmic sense, it's not the giants that endure. It's the quiet ones, the overlooked ones, the small, slow-burning stars that never tried to light up the whole galaxy, but just kept glowing. Maybe there's a lesson in that. We tend to admire the brightest stars, the boldest lives, the biggest impacts. But sometimes, survival isn't about burning bright. It's about burning long. Wolf 359 will never be a celestial celebrity. You can't even see it with the naked eye. But its story might outlast every visible star in the sky. And in the deep time future, when the universe is cold, dark, and silent, its memory might still whisper across the cosmic void. I was here.
And I endured. So, if Wolf 359 is destined to be one of the final embers of a dying universe, what comes after that? Well, that's where things get really weird. We're talking heat death, proton decay, quantum tunneling, concepts so abstract, even the laws of physics get a little fuzzy. But whatever happens in that far-off epoch, one thing's for sure. Wolf 359 will have lived longer than anything we can imagine. And that makes it more than just a star. It's a monument to cosmic patience. Now you might be thinking, if something that tiny can last that long, what else is hiding in the universe that we haven't given a second glance? Well, up next, let's zoom in closer to this mysterious star. Because while it's ancient and enduring, Wolf 359 isn't just a passive observer. It's alive in its own way. It flares, it storms, it crackles with magnetic energy. In fact, it might be more dangerous than it looks. So let's say, just for a moment, we hit the cosmic pause button. We zoom way, way out, past our busy little planet, past the swirling dance of galaxies, and out into the far, cold reaches of time. What's still out there? Ticking. If you guessed Wolf 359, give yourself a cosmic gold star. Because while stars like our sun live fast and die in a blaze of glory, Wolf 359 is in no rush. It's not here for the drama. It's the quiet, slow-burning candle in the corner of a vast, dark room. And that might just be its superpower. You see, red dwarfs like Wolf 359 are masters of cosmic minimalism. They burn their hydrogen slowly, agonizingly slowly, like a miser who stretches every last penny. And it's not because they're weak. It's by design. Their cooler temperatures and lower masses mean they don't burn through their fuel the way bigger stars do. Let's put that in perspective. Our sun, it's got a decent shelf life, around 10 billion years. We're about halfway through that. But Wolf 359, it's planning a cosmic retirement party in, brace yourself, up to 10 trillion years. That's not just long, that's end of the universe long. By the time Wolf 359 runs out of fuel, entire galaxies will have faded. The night sky we know today? It'll be ancient history. It's like watching someone nurse a single candle for millennia while bonfires around them burn out one by one. Now, here's where things get weird. Imagine the universe tens of trillions of years from now. The cosmos isn't young and sprightly anymore. It's gone grey. Galaxies have thinned out. New stars, not really being born anymore. The party's over. Black holes dominate the landscape, slowly evaporating through Hawking radiation. The temperature of the universe creeps closer to absolute zero. Everything is quiet, still, and in this vast, cold silence, Wolf 359 is still glowing. Faint, yes, but stubbornly there. It's like the universe is a theater, and after the show ends, the crowd leaves, the lights dim, and in the back row, there's this one old soul still watching, waiting for the credits to finish rolling. So what gives these tiny stars such absurd longevity? It comes down to how they burn their fuel. Most stars, like our sun, only use the hydrogen in their cores for fusion. That's it. Once it runs out, boom, giant red phase, then collapse, then the end. But red dwarfs? They mix things up, literally. They're fully convective. This means they stir their insides like a pot of soup, constantly cycling hydrogen from the outer layers into the core. No wasted fuel, no excess, nothing left behind. That efficient design means they burn all their hydrogen, slowly, methodically, over trillions of years. It's like a car that not only gets 1,000 miles per gallon, but also refuels itself by cycling gas back into the tank. And because of this, red dwarfs like Wolf 359 will be the last stars shining. Not just among the last, period. Long after humanity is gone, long after Earth is swallowed by the sun, long after the Milky Way and Andromeda collide and reshape themselves, Wolf 359 may still be quietly glowing, keeping the night just a little less dark. Even time itself seems to stretch differently for a star like this. While we measure centuries and decades, Wolf 359 measures in epochs and eons. So what happens at the end of 10 trillion years? Well, no explosion, no supernova, no drama. Wolf 359 will gently fade into a white dwarf, and then, over trillions more years, it will cool, slowly turning into a black dwarf, a cold, dark cinder adrift in a frozen universe, a ghost of a star, not even emitting light anymore, just there. But here's the kicker. No black dwarf has ever existed yet. Not one. The universe simply hasn't been around long enough for any star to live that long and die that slow. So Wolf 359 and its red dwarf cousins are writing a future we haven't even seen yet. They're the great-grandparents of time, patiently waiting for the final chapters of the universe to begin. There's something humbling about that, isn't there? In a universe obsessed with speed, explosions, and brightness, Wolf 359 reminds us that sometimes the quietest voice is the one that endures the longest. It won't headline the news. It won't go supernova or make spectacular nebula art. But it'll still be there long after the loud ones burn out. In a way, Wolf 359 is like the ultimate survivor. Not through strength, but through patience. Not by shining the brightest, but by glowing long after the rest are gone. And maybe, just maybe, there's a lesson in that. About persistence, about endurance, about playing the long game. Because while our own world is fragile, short-lived, and always changing, out there, 7.9 light-years away, there's a tiny red dwarf planning to outlive galaxies. And that brings us to one final strange idea. What if one day, somewhere unimaginably far into the future, a distant civilization emerges from the ashes of a dead universe, and the first light they see is Wolf 359. But even with its cosmic endurance, Wolf 359 still holds mysteries. And while it might never explode, that doesn't mean it can't surprise us. Okay, so we've spent a lot of time talking about how Wolf 359 is basically the chill grandma of the cosmos. Quiet, slow burning, minding its business in the galactic suburbs. But what if, just if, it wasn't as harmless as it looks? What if that tiny red speck in the sky turned against us? Let's start with something simple. Wolf 359 is close, just 7.9 light-years away. That's basically next door on a cosmic scale. If the Milky Way were the size of Earth, we'd be in the same neighborhood, like walking distance. Now, 7.9 light-years might not seem like much of a threat, but when you're dealing with massive objects like stars, even the tiniest gravitational influence can matter. A nudge here, a wobble there, and entire planetary systems can be thrown into chaos. So if Wolf 359 started moving toward us, even at a fraction of the speed of light, we'd notice. And fast. But how could that even happen? Well, space isn't as calm as it looks. Stars move. They orbit the galaxy, get kicked by gravitational slingshots, jostled by passing bodies, or, on rare occasions, flung out of their star systems entirely. They become what astronomers call rogue stars, lone travelers, homeless, drifting. So imagine Wolf 359 gets nudged, a supernova somewhere nearby, a rogue planet crashing through, or just the subtle, invisible tug of a massive object we haven't detected yet. Suddenly, this little red dwarf is drifting toward us. Now, let's be clear. Wolf 359 isn't going to explode. It's not a ticking time bomb like a white dwarf might be, but it has something arguably worse if it ever came too close. Gravity. Imagine it slices through our solar system like a bowling ball through a sandbox. Planets pulled off their orbits, comets sent flying, tidal forces tugging on Earth's crust. Even if it didn't hit us directly, it could disrupt the Oort cloud, the massive shell of icy objects surrounding our solar system. That could send a rain of comets hurtling toward Earth, a cosmic hailstorm that could last thousands of years. And we probably wouldn't see it coming until it was way too late. Here's another wild thought. What if Wolf 359 isn't what it seems? Because here's the thing. Red dwarfs are dim. Extremely dim. If Wolf 359 had a dark companion, say a black hole orbiting beside it, we might not even know, not unless we were looking very closely. There are already candidates for dark binaries like this in our galaxy. Red dwarf plus black hole tag teams that are nearly invisible from Earth. Now imagine Wolf 359 has a hidden companion like that. A black hole, quietly orbiting, undetected. If it passed through the right part of space, it could start feeding, accreting matter, waking up, and then, suddenly, we've got a red dwarf and a feeding black hole barreling our way. Science fiction? Sure, but not impossible. But maybe the threat isn't Wolf 359 directly. Maybe it's what it causes indirectly. You've heard of tidal locking, right? That's when one side of a planet always faces its star. Well, red dwarfs tend to do that to their planets. So, if we ever colonized one of its hypothetical exoplanets, we'd be living in extremes. One side blazing hot, the other eternally frozen. But it gets worse. Red dwarfs are known for flare activity, sudden bursts of radiation from their surfaces. And while Wolf 359 isn't one of the worst offenders, it does have magnetic storms. Picture a solar flare so powerful it fries every satellite, every electronic system on a future colony in seconds. Communications gone, power grids down, radiation storms battering the atmosphere. It's the cosmic version of a moody hermit suddenly flipping the table. And here's the biggest twist of all. What if it's not about us fearing Wolf 359, but needing it? Because in a few billion years, when our own sun expands and swallows Earth, we're going to need a new home. Something stable, long-lived, not prone to violent outbursts. And guess what kind of stars fit that bill? Yep, red dwarfs. Even if Wolf 359 is a little grumpy or carries some hidden dangers, it might still be a better landlord than a dying sun. The threat might be the invitation. So, will Wolf 359 one day drift into our system and ruin everything? Will it hurl comets at us, pull Earth off its axis, or unleash a hidden black hole on our neighborhood? Probably not. But could it? Well, the universe is a very big place, and it's been around for 13.8 billion years. Long enough for some very strange things to happen. And when it comes to Wolf 359, this dim, quiet, unassuming star just down the road, we'd be wise to keep an eye on it. Because in the great galactic poker game, even the smallest players can change the game. But whether Wolf 359 stays silent or surprises us, one thing's for sure: it's not done telling its story, and neither are we. You know, for a star that's only about the size of Jupiter, Wolf 359 sure carries a lot of cosmic mystery. It's like the unassuming house at the end of the street, quiet, dimly lit, barely noticeable, yet you can't help but wonder what's going on inside. And that curiosity brings us to a big question, one that tiptoes along the line between science and sci-fi. Could Wolf 359 be hiding something? Something artificial? Let's say you're an alien civilization. You've made it past your species' awkward adolescence, wars, climate disasters, social media debates, and you're ready to harness the power of your entire star. Where do you start? That's where the idea of megastructures comes in. And no, we're not talking about giant Death Stars or solar-powered coffee makers, though who knows? We're talking about something far more ambitious, something like a Dyson sphere. Now, the Dyson sphere isn't a solid shell wrapped perfectly around a star like some giant Christmas ornament. That's the sci-fi version. In real, theoretical science, it's more likely to be a Dyson swarm, a vast cloud of solar-collecting satellites orbiting the star like bees around a hive, sipping energy instead of honey. Or maybe a Dyson bubble with reflective sails capturing and redirecting starlight. Or, if you're into literary sci-fi, something like a Niven ring, an enormous ring-world structure that spins around a star to simulate gravity. Kind of like putting an entire civilization on a space racetrack. These concepts aren't just daydreams. They're serious ideas in theoretical astrophysics, our best guesses at what extremely advanced civilizations might build once they outgrow planetary limitations. And here's where it gets even more interesting. They wouldn't build these megastructures around just any star. They'd want a star that's stable, quiet, long-lived, something that won't explode or fizzle out in a few million years. And guess what kind of stars fit that bill perfectly? Red dwarfs. Stars just like Wolf 359. Now, imagine this. You're a civilization that thinks not in centuries or even millennia, but in millions of years. Your homeworld has already burned through its own star, or maybe it never had a star bright enough to begin with. You migrate, you search, and eventually, you settle near a red dwarf. Why? Because red dwarfs like Wolf 359 burn slow. They sip their hydrogen instead of guzzling it. Some could last for trillions of years. That's longer than the current age of the universe. In cosmic terms, red dwarfs are the ultimate slow cookers, perfect for civilizations that aren't in a rush. They're dim, yes, but that's not a problem if you've built giant solar collectors or light-harvesting mirrors to amplify the glow. And that dimness, that might actually be a feature, not a bug. See, a megastructure built around a bright star like our Sun would have to contend with massive radiation, flares, and energy output. But a red dwarf, it's easier to manage, and the low light makes it easier to hide what you're doing from distant onlookers, like us. So how would we, sitting here on Earth, even know if someone's been remodeling Wolf 359? We'd look for techno-signatures, clues left behind by advanced technology, even if we can't see the structures themselves. One possibility is an infrared excess. If someone built a Dyson swarm around Wolf 359, it would capture light and energy, but it would also radiate heat, especially in the infrared spectrum. Think of it like a giant cosmic radiator glowing softly in a frequency our eyes can't see, but our telescopes can. We could also look for strange dimming patterns, uneven, unnatural dips in the star's light that don't match what we'd expect from orbiting planets. That's how the whole Tabby star mystery began. A star that flickers unpredictably, sparking speculation about alien megastructures, even though dust seems more likely now. But what if a civilization didn't want to be seen? They might use stealth tech or build in a way that blends into the star's natural light profile. They could angle their collectors to reflect light back toward the star, hiding any infrared leakage. Invisibility at an interstellar level becomes a game of thermal camouflage. Still, if even one civilization slipped up, if we caught just one little flicker of artificial engineering, that would change everything. This brings us to the Kardashev scale, a way of ranking civilizations based on how much energy they can use. Type 1, planetary civilizations, like us, barely. Type 2, stellar civilizations, capable of harnessing the energy of an entire star. Type 3, galactic civilizations, controlling the power of countless stars across entire galaxies. A Dyson sphere? That's the ticket to Type 2. And if Wolf 359 had something like that orbiting it, we'd be staring into the next chapter of intelligent life in the universe. Not just, is there life out there, but how much more advanced could they be? Here's the catch, though. Despite its relative closeness, just 7.9 light-years, Wolf 359 is still faint. It's not something you stumble across accidentally. You have to look for it, specifically. And that makes it a symbol of something bigger. Not just of what might be out there, but of what we might be missing. It's kind of poetic, isn't it? We focus so much on big, bold stars and flashy supernovae. But what if the real treasure, the real secrets of the cosmos, are hiding in the dark? What if the quietest stars are the most interesting? Wolf 359 reminds us to look closer, to question the shadows, to wonder about the light that's missing, not just the light we see. And maybe, just maybe, that's the point. Not to prove that Dyson spheres do exist around red dwarfs like Wolf 359, but to let our curiosity roam freely enough to ask the question in the first place. Because when we ask those questions about life, energy, the scale of intelligence, we start to see ourselves a little differently too. Not as the rulers of a planet, but as potential neighbors in a vast galactic neighborhood. And whether or not Wolf 359 hosts a hidden alien empire orbiting silently behind a veil of engineered shadows, we'll keep watching. Because the search for answers isn't just about finding aliens, it's about understanding what's possible, out there and right here on Earth. So the next time you step outside and stare up at the stars, remember, some of the most incredible stories might be unfolding in places you can't even see, like a tiny red dwarf, quietly burning, patiently waiting, just 7.9 light-years away. So, we've talked about the possibility of alien megastructures orbiting around red dwarfs like Wolf 359. But let's pull the camera back for a second. Way back, past our solar system, past the stars we can name, past the edge of the familiar. Now ask yourself this. If humanity ever leaves Earth behind for good, where do we go? What kind of stars will light the path for our interstellar future? If your mind immediately jumps to bright, powerful stars like Sirius or Rigel, I've got news for you. They're not the best bet. In fact, some of the smallest, dimmest stars in the sky, like Wolf 359, might just be our cosmic stepping stones. Let's start with the obvious question. Why would we aim for a tiny red ember like Wolf 359 instead of a blazing giant? Well, for one thing, red dwarfs are the cosmic equivalent of the slow-cooked meal. They burn fuel so efficiently that they'll outlive most other stars in the galaxy. Wolf 359? It's already over 1 billion years old, and it could easily last another 10 trillion. Yeah, trillion. With a T. That's not just long-lived, that's cosmically immortal. And for a species like us, who are just getting our spacefaring sea legs, longevity matters. We're not looking to crash the party of some hotshot blue star that's going supernova in a few million years. We want a stable neighborhood, one where we can build, grow, maybe even call home. Red dwarfs as galactic pit stops. Now imagine this. Generation ships, Massive vessels carrying entire communities of humans, gliding silently through the void for hundreds, maybe thousands of years. Their destination? Not some flashy star 100 light-years away, but the nearest red dwarf system within reach. Why? Because red dwarfs are everywhere. They make up about 75% of all stars in the Milky Way. They're not rare, exotic, or hard to find. In fact, they form this incredible interstellar web, a cosmic chain of rest stops dotting the galaxy like mile markers on an endless highway. If we ever attempt to spread outward, we might not make giant leaps from one solar twin to another. We'll island hop across red dwarfs, slowly, deliberately, patiently. That might sound less glamorous than warp drives and hyperspace lanes, but it's realistic and strangely beautiful. Power, light, and a place to breathe. Here's the other thing. For all their faintness, red dwarfs don't skimp on energy. They emit light, just not much in the visible range. But in infrared, they're buzzing. Warmth, radiation, a steady stream of energy, perfect for solar collectors or advanced power harvesting tech. And because they're so calm, rarely flaring after their early years, they offer a stable, low-stress environment for long-term colonies, especially if those colonies are parked on tightly orbiting planets or in orbital habitats basking in the soft, steady glow. Unlike the Earth, which takes 365 days to circle the Sun, planets around red dwarfs often orbit in weeks or even days. That means shorter years, faster seasons, and maybe even tidally locked worlds, where one side always faces the star in perpetual daylight and the other remains forever in night. It's alien, strange, but not necessarily unlivable. In fact, with the right tech, it could be ideal. Picture a generation ship from Earth arriving at Wolf 359 in the distant future. It's been cruising through interstellar space for centuries. Most of its passengers have never even seen Earth, only heard about it in stories passed down from great-grandparents. The ship pulls into orbit around this faint red star. It's not much to look at, barely visible from the observation deck. But it's steady, and it's home now. They deploy massive solar sails to start harvesting energy. They launch drones to scan for icy moons, asteroid belts, or even terraformable planets. Then they start to build. Maybe not cities at first, but orbital habitats, spinning gently in the dark. Artificial gravity, self-sustaining life systems, slowly growing hydroponic farms. From that point on, Wolf 359 isn't just a name in a database. It's a colony, a seed, a human outpost among the stars. And eventually, it becomes a launching pad for the next hop, the next red dwarf, the next dream. This is the big idea, one that's been gaining traction among scientists and sci-fi writers alike. Instead of blazing across the galaxy in a frenzy of expansion, humanity could embark on a slow, methodical wave of colonization. Red dwarf by red dwarf. Each system becomes a node, a beacon, a foothold. And once we've mastered living around one, adapting to another becomes easier. And because red dwarfs are so long-lived, each colony has billions, trillions of years to thrive, to evolve, maybe even to forget where they came from. It's not flashy, it's not fast, but it's sustainable, it's smart, and it's possible. The science behind the scenes. This isn't just science fiction dreaming. There's actual science backing it up. Studies from SETI and other research groups have explored the idea of life around red dwarfs, not just alien life, but our life. They've looked at planetary habitability, energy availability, stellar radiation, and what they've found is surprisingly hopeful. If planets orbit in the habitable zone, close enough to stay warm but far enough to avoid frying, they could absolutely support life, human or otherwise. Yes, there are challenges: tidal locking, potential flares, limited light, but none of them are deal breakers. In fact, many red dwarf systems are already on NASA's exoplanet watch list, including Wolf 359. We haven't found any planets there yet, but our instruments are getting better every year. And if something's out there, something rocky, warm, maybe with a thin atmosphere, we might spot it soon. And then the real planning begins. From local dream to galactic reality. So what does this all mean? It means that stars like Wolf 359 aren't just cosmic curiosities. They're not just trivia answers or placeholders on star charts. They're opportunities. They're gateways. They offer the chance to build slow, resilient civilizations, to outlast even the brightest stars, to reshape what colonization looks like, not as conquest, but as patient planting. Red dwarfs might not light up the sky like Betelgeuse or Vega, but they burn with the fire of forever. And in the long game of galactic exploration, that's exactly the kind of star you want on your side. Now, you might be wondering, if red dwarfs are so ideal, could we already be missing the signs? Could ancient civilizations have already settled around them? That brings us to something even more mysterious. What if these stars, quiet, unassuming, flickering in the shadows, are already home to advanced life? And what if we've been looking right at them and just didn't know what to look for? Now that we've seen why red dwarfs like Wolf 359 might one day be humanity's first cosmic pit stops, let's take a step back and peer even deeper. Not with our eyes, but with something even more powerful: chemistry. Because if you want to know the true nature of a star, its past, its potential, even its personality, you need to look at what it's made of. What elements are swirling and fusing within that little ember in the sky? What story does its chemistry tell? Let's imagine for a moment you're holding a prism up to starlight. Just like that rainbow that appears on your wall when sunlight hits glass at the right angle, this star's light can be broken down, dissected, into a cosmic barcode. A barcode made of colors, each one corresponding to an element. Hydrogen glows a certain way. Helium? Slightly different. Even heavier elements like calcium, sodium, and iron leave behind distinct scars on the light. We call these absorption lines. Think of them as a star's passport stamps, the marks of where it's been and what it carries. Now, Wolf 359 doesn't exactly have a rich passport. It's mostly carrying light luggage. Hydrogen is the dominant element, as it is in all stars. After all, hydrogen is the most abundant element in the universe. It's the cosmic starter pack. Along with helium, it makes up over 99% of what Wolf 359 is. But here's where it gets interesting. Tucked in between those two lightweights, hydrogen and helium, there are traces of what astronomers refer to as metals. Not heavy metals like Iron Maiden or Metallica, but in astronomy, anything heavier than helium counts as a metal. And Wolf 359 is not very metal. Compared to our Sun, which has a fair bit of these heavier elements, carbon, oxygen, iron, Wolf 359 is what we'd call metal poor. It has low metallicity, which is just a fancy word for how many of the good bits it picked up when the galaxy was young. See, stars are kind of like generational stories. The earliest stars, born just after the Big Bang, were almost pure hydrogen and helium. They lived fast, died young, and in their explosive deaths, they created the heavier elements: carbon, silicon, iron. The stuff we're made of, the stuff planets need to exist. Then, new stars formed from the ashes of those first stars, carrying just a bit more of that complex chemistry. And that process has continued, generation after generation, until stars like our Sun were born in a more enriched neighborhood. But Wolf 359? It seems to have come from an older part of the galaxy. It has lower metallicity, meaning fewer of those building blocks. It's like a minimalist apartment, functional, but not exactly furnished with fine china. And yet, don't let that fool you, because even this little red ember carries whispers of ancient supernova, long-dead giants that seeded the interstellar medium with the elements Wolf 359 now carries. Spectroscopy, the science of analyzing a star's light, has revealed hints of calcium, iron, magnesium, even sodium in Wolf 359. These trace metals may be few in number, but they're incredibly revealing. For one, they suggest that this star was formed early in the Milky Way's timeline, perhaps over 7 billion years ago. That's older than our Sun. Maybe not quite an elder of the galaxy, but certainly from a more ancient epoch, when the cosmic pantry was still pretty bare. And that makes Wolf 359 something of a living fossil, a low-mass, slow-burning relic that has been silently glowing since before Earth even existed. Its chemistry? A snapshot of what the galaxy had to offer at the time it was born. Now here's where the rabbit hole deepens. What does Wolf 359's chemistry mean for the potential of planets? Well, stars with high metallicity tend to form more complex planetary systems. That's because rocky planets, like Earth, need those heavier elements. No metals, no iron core, no tectonic plates, no atmosphere. And while gas giants can form with less metal content, a rocky Earth-like planet is much harder to sculpt from the cosmic dough without iron and oxygen and silicon. So, if Wolf 359 is metal poor, does that mean it can't have planets? Not necessarily. We've discovered plenty of red dwarfs with planets, even ones with low metallicity. And in fact, the sheer number of red dwarfs, combined with their long lifespans, means they may host a huge portion of all planets in the galaxy, metal-rich or not. Think of it like this. Even if Wolf 359 isn't baking 5-tier wedding cakes, it might still be making some humble but hearty cookies. Small, simple planets. Maybe not Earth 2.0, but perhaps Earth 0.6. And here's something truly fascinating. The chemistry of a star doesn't just tell us about the potential for planets, it also hints at the habitability of those planets. For instance, stars that flare frequently, like many red dwarfs, can bathe nearby planets in harmful radiation. But Wolf 359, while known for occasional flares, isn't the wildest of its kind. Its chemical makeup lacks the high-energy emissions we see in more massive, unstable stars. It's faint, it's stable, it's slow, and from a habitability standpoint, that's actually promising. If a planet were to form around Wolf 359 and settle into the right distance, the so-called habitable zone, it could theoretically enjoy a very long life. Red dwarfs live trillions of years. That's more than enough time for life to evolve, adapt, and thrive if the starting ingredients are right. Which brings us full circle, right back to chemistry. Because as quiet and dim as Wolf 359 may seem, it is still a crucible. Its fusion engine is constantly turning hydrogen into helium, releasing energy, shaping magnetic fields, and whispering clues about its inner life into the cosmos through the language of light. And here's a thought experiment to chew on. If you could scoop up a spoonful of material from the core of Wolf 359, just a teaspoon, you'd be holding something denser than any metal on Earth. Plasma hotter than anything in our solar system. Elementally simple, yet impossibly ancient. You'd be holding the ashes of the universe's youth, and maybe, just maybe, the promise of its future. Because here's the final twist in the tale. As the galaxy continues to age, red dwarfs like Wolf 359 won't just become more common, they'll become the norm. Billions of years from now, after stars like our Sun have burned out, red dwarfs will still be out there, glowing softly, stubbornly alive. So in many ways, understanding the chemistry of Wolf 359 isn't just about understanding one star. It's about glimpsing the future of starlight. So here we are, at the end of our strange little cosmic road trip. From the outside, Wolf 359 still looks like, well, nothing much. Just a faint blip. You can't see it with the naked eye. You might have never even heard of it before today. And yet, in just the past few minutes, we've watched this unassuming red dwarf go from cosmic footnote to galactic wildcard. A star no bigger than a planet, darker than your darkest night. And yet, somehow, it leaves behind a legacy bigger than most stars ever will.
Let's take a step back and reflect. There's something poetic about Wolf 359, a star that spent most of its existence in obscurity, never flashy, never loud, just doing its thing, out there in the dark. It wasn't the first star discovered, not the brightest, not the most explosive. It's not the source of ancient myths or the centerpiece of some awe-inspiring constellation. For most of human history, Wolf 359 was invisible to us, literally. It wasn't until the 20th century, with better telescopes and sky surveys, that we even spotted it. And even then, it didn't get much love. No viral headlines, no top 10 coolest stars articles. Just a boring red dwarf in a boring part of space. But isn't that kind of beautiful? Because in many ways, that's where the real magic happens. Wolf 359 reminds us that the universe doesn't always shout. Sometimes it whispers. And if we're too busy chasing the big, bright, burning things, we miss the quiet wonders, the steady flames, the small lives, the hidden stories. In a sky full of giant stars that burn out in dramatic supernovas, Wolf 359 is playing the long game. It's not here to shine, it's here to last, and that's its legacy. Let's think about that for a second. If we ever leave Earth, really leave it, we won't be looking for bright, hot stars like the sun. They're too unstable, too short-lived. We'll be looking for red dwarfs, stars like Wolf 359. They burn low and slow. They sip their hydrogen instead of guzzling it. They can last trillions of years. That's right, trillions. Our sun is halfway through its measly 10 billion year lifespan. Wolf 359, barely getting started. It'll still be here long after the sun has puffed up into a red giant and swallowed Mercury, Venus, and maybe even Earth. So in the cosmic relay race, Wolf 359 isn't the sprinter. It's the marathon runner, pacing itself, going the distance, outliving almost everything. And if humanity sticks around long enough, Wolf 359 might be the kind of place we look to when Earth is no longer home. There's something deeply human about this whole story. We spend so much time looking at what's right in front of us, what's brightest, what's loudest. And yet, some of the most profound truths about life, time, and survival are hiding in the background. Wolf 359 is a reminder of that. For decades, we ignored it, because it didn't look important, because it didn't demand our attention, because it wasn't shiny. But in the silence of space, in that tiny speck 7.9 light-years away, lies an entire universe of lessons. That endurance doesn't always come with applause. That power doesn't always look like explosion. That just because something is quiet doesn't mean it's not significant. Let's be honest. If Wolf 359 were a person at a party, it'd be the one leaning against the wall, sipping something non-alcoholic and not really saying much. You might walk past them a dozen times before realizing, wait, this person knows more about the universe than anyone in the room. And that's how science works sometimes. The breakthroughs, the big ideas, they don't always come from where you expect. Sometimes they're tucked away in a dim red dot just outside your line of sight. Maybe that's why Wolf 359 hits a little deeper than most stars, because in a strange way, it mirrors us. Small in the grand scheme of things, easy to overlook, but filled with untapped potential. Think about it. This tiny star has survived for billions of years and will likely exist for trillions more. And it's only recently that we've started to understand even a fraction of what it is and what it means. How many things, people, ideas, right here on Earth, do we overlook every day in the same way? Maybe the real legacy of Wolf 359 isn't just about astronomy. Maybe it's about attention, about what we choose to see, and what we might be missing when we don't look closely enough. Here's the strange twist. Red dwarfs like Wolf 359 are the most common type of star in the galaxy. They make up over 70% of all stars, and yet most of us couldn't name a single one. That's like being surrounded by the same type of tree all your life
and never asking what it is. But the more we study stars like this, the more we realize they're the norm, not the exception. If alien life exists out there, chances are high it's orbiting a red dwarf, maybe even one like Wolf 359. Maybe we've been looking in the wrong places this whole time. Now you've heard the story of the star with a forgettable name and unforgettable endurance. The red dwarf that's barely visible, and yet impossible to ignore once you learn what it truly is. Wolf 359. It didn't ask for fame, it didn't explode to make a point, but somehow, without trying, it's left a mark. It's taught us that the universe isn't just fireballs and bangs, it's layers, it's time, it's patience. And maybe, just maybe, that's the kind of legacy we should aspire to too. So the next time you're under a clear night sky, take a moment, not to find Orion's belt or chase down Venus, but just to look, to wonder what's out there, just beyond your vision. Wolf 359 is out there, quiet, steady, waiting. And it's not the only one. There's a whole universe of stories like this one. Tiny stars, forgotten moons, rogue planets, silent signals, all waiting for someone curious enough to ask, what else have we been missing?